The next tutorial will start in approximately 20 minutes. We start in approximately 10 minutes. I was muted. Thank you, Kristen, for letting me know. And also Anna Carla and Matteo. Thank you so much, folks. So I will repeat. Now, welcome to the second tutorial of ADAS 2020 and also the second time slot. And we have a fantastic tutorial in just a few minutes by Humberto, is joining us from Chile. And Humberto is online. I can see him. I'm in contact with him in Discord, and he will join us in just a few minutes. He's getting his computer ready, or he's set up, and things like that. While we wait, I will just do some Zoom administration stuff here, but I will be back in just a second. And, you know, if Humberto doesn't join exactly on time, I have very bad jokes ready. So we have somebody with the hand up, Rosa. Okay, that's our room manager. And I will get back. And there is Humberto. Humberto, you know, Humberto, I had a fantastic bad joke ready, but I will save it for the next tutorial. So Humberto, you're joining us from Chile. Is that right?
Yes, it's correct.
Awesome. What time is it over there?
8 o'clock in the morning.
Whoa. I hope you had a good coffee.
Yes.
Awesome. So Humberto, you're talking about from semantic segmentation to image instance segmentation using deep learning. I'm very excited about your tutorial. I see you already sharing your screen, so I will let the stage for you, and I will get out of your way.
Thank you, Francesco. First, my name is Humberto Farias. I am from Chile. I am PhD candidate of University Santa Maria. Also, I will work in the Chilean Virtual Observatory. And also, I am part of the data science group in University of La Serena, also in Chile. Like the tutorial say, today we talk about deep learning applied to astronomy, especially in the task of semantic segmentation, classification and location, object detection, and instance segmentation. These are all tasks in computer vision, but applied with deep learning architectures. In the image that you see, I share first. I share the link of the notebook that you can follow me when I show the process to implement these networks. And the image that you see, these are the 4 main tasks in astronomy applied to the the 4 main tasks of computer vision applied to astronomy. The first is classification. In this task, you have your input is an image, and you want to know if in that image you have a certain object. The second task is semantic segmentation, and semantic segmentation is given an image, can we classify each pixel as a belonging to a particular class? The second is object detection. Object detection is a more general case of the classification and location problem. In the real world setting, we don't know how many objects are in the images beforehand. So can we detect all the objects in the image and draw the bounding box around them? That is the main goal of this task. And finally, and the more powerful architectures are semantic segmentation, instance segmentation. And the goal of this task is, can we create a mask from each individual object in an image? Is different from semantic segmentation because here we can have different instances of different class. For example, if we in this image we have two galaxies, but the galaxies are detected individually, are different from the semantic segmentation that we identify a galaxy in the general scope. But there is plenty architectures to apply to semantic segmentation. The more powerful and known is U-Net. U-Net is a full convolutional neural network. The reason behind why it is named a U-Net is because of the shape of this architecture. The model, like you see in the image, the model looks in the shape of a U, and so the name has been derived from it. There is two main parts of the U-Net model. One part is the contraction part, or the encoder, which is the left side of the model, and the other is the expansive part, or the decoder, which is the right side of the model. You enter an image from the model, and we start with the contraction path. As a result, your data has been compressed in code in a few variables. From this higher representation, the network try to reconstruct the code, the input again. It is an end-to-end fully convolutional network. What is the meaning of this? This means that they only contain convolutional layers and does not contain a dense layer, because of which we can accept the training and testing or images of any size. This is important because the traditional CNN or convolutional neural network have a finally output layer that is a dense layer that with, for example, activation function as a softmax to difference from, for example, this is a galaxy with 90%, for example, and the case of U-Net don't have a dense layer, only because the goal is to segmentate or separate a certain galaxy or object from the background in the image. Like I say, the first part of the U-Net architecture is a set of convolutions with a pooling that downsize the image resolution. Because of that, this is the name of the contraction block, and create additional layers to extract features from the original image. The contraction path consists of repeatedly applying two convolutional layers for three unpadded. The convolutional layer is followed by the ReLU, the rectified linear activation function, and max pooling of 2 for 2 with a stride of 2, like we see in here. We start from the left side, we downside our image, we are encoded our image, and next we start with the decoder. It's also a network that takes the feature from a vector form to the encoder and gives the best closest match to the actual input or intended output. This is usually the same network structure that the encoder, the left side of the U, but in an opposite direction. We are a contraction path and expansion path in the right side. The expansion path consists of output convolution, the 2-for-2, also known convolutional transpose for upsampling. The up convolution reduces the feature map by the half. Later, the result is concatenated with the counterpart from the contraction path after cropping. Similar to the contraction path, the layer ReLU that is followed by after 2 consecutive convolutional layers. And for example, here, for the intuition behind the model, given an input image, in this case, a galaxy, elliptical spiral galaxy. In this case, we have a RGB image of a galaxy. The UNet model produces a binary mass of ones and zeros, where 1 indicates a galaxy and 0 indicates a background, including in this the borders between the galaxy. Note that this is a semantic segmentation task because all the galaxies receive the same label of galaxy, because in this model that we work in this tutorial, we only want to separate a galaxy class from the background. And this is the general or the big picture, the general introduction to the UNet. In the tutorial itself, the first thing we need to do is to check if we have activate the GPU support for our notebook. Like you see in the notebook, you need to go to the runtime here and enter to the change route time type. For example, I have the GPU support activate. You need to do the same in your notebook. And then we run the set, and we check that the notebook found a GPU at this location. Second, we need to import our libraries to implement a simple version of UNet. We will use TensorFlow. We run this. And also we can check that we have a 1 GPU available for our work. The next task we need to perform before we start to implement our model is to mounting the Google Drive locally. It's important we see that you can mount your Google Drive file by running this code. And we need to go to this URL to give the permission to our notebook to access our data. I select my account and go to, in my case, permitted, because it's in Spanish. We need to copy this code and put the code here and press enter. And now we are ready to use our drive space in Google for storage and process our model. We check that we have the access to our Google Drive. Yes, in my case, I can. Next, you need to create the folder for the tutorial in your drive. in my case, I think that I created before. Yes, yeah, I have created before. In your case, you don't have these methods. You can also check if you have the folder created in your drive, access from the left panel, and check here, drive, my drive, and the folder for the tutorial. In my case, I have more files because obviously I prepared this tutorial. Well, the overview of all the deep learning models or the life cycle to implement a model in deep learning follow these 6 steps. Before the first one is downloading and analyze the dataset. Second is prepare the datasets. And next, create the model, compile the model, fit to the model, and finally evaluate the model and the results over validation part of the dataset. The first thing we need to do is to download the datasets. This dataset has this form. We have a folder with the image. This is a JPA image from images and the spiral and elliptical galaxies. And also we have a directory with the mask. That is a PNG grayscale image. That is the ground truth or the segmentation to the correspondent image in the first folder. Because to train our model, we need to enter the image and also the mask to the network learn to generate automatically this segmentation mask. First, in my case, I will check I have the 2 folders. You need to download and comment this this command and run it.
Okay, looks like Humberto's connection dropped. These are the problems in an online meeting. So let's wait a couple of minutes for him to come back online. I'm sure it will not be long. Okay, Humberto is already back. Yeah.
Sorry, but with the pandemic, we have a connection problem in Chile. Here, and now online again. Yes, we start again from the mountain my drive. And it's okay. And check if the files are correctly mounted. Yes. Next, we need to analyze our data set. The image are has 3 channels, are RGB image that 266 for 266 pixels, and the PNG's mask only have a 1 channel because is only 1 and zeros that has the form to the segmentation. We need to define the root directory path and that folders to access that folders. And this is our task to define the path to our data set. We define the size of the data. You need this is a compressed version of our data, and also we have 3 channels because it's a RGB image. This is all the parameters you need to configure before the running the network. And need to sorting and compress the input to our model. And like you see, we have around 172 images. This is a toy data set because we have a limited capacity to perform the tutorial in Colab. Obviously, you want to, for training any deep learning model, like you need to have more examples of your data. Now we need to check that our data has this form. For example, I have the original image, and this is a mask for the corresponding image. Is the same. This is important, obviously, because we need to enter the image and the corresponding mask for that image for the unit learn the model. And for example, this is how I look our data. This is the original image, and this is the mask we use as an input to our model. And in the case of the mask, we have only 1 channel. Next, we need to create the data loader class. This is because we use TensorFlow. If you use PyTorch, for example, you have a different data loader. But because we use TensorFlow, we use this class to read our data sets. We need to run this code. And right now we are start to define finally our architecture. The first step is to create the input. The input has the shape of the size of the image and also the 3 channels of the image. And it's okay. The 3 channels and the size of the image. Compressed like I said before. The contraction path is like I said before, is the goal of this path is to reduce the size of our image in the way to find to destacate the main features in the image. And we start the first part of the contraction part. And okay, this is all the verbose that the model show that when we create these layers. And next we have the filters, the 3 filters that that is we start with 64, 128, 28, and so on. We run this code. And it's okay.
So Umberto, I'll just interrupt you just a second. Do you want me to read the questions? There are a couple of questions.
Yeah, I read that they have the problem with the folder.
That's correct, yes.
I will check. Okay. Give me a second. I need to check my stream.
So just for everybody else watching on YouTube, there was an issue reported by a couple of people saying that in the downloads there were different folders or not exactly a correct folder. So Umberto is checking right now to make sure that everything is cool.
I need to check this. Okay, give me a second. I need to check this. I will continue before finishes. But I'm pretty sure that is the correct answer. I don't know. Well, we have also a class of using S3 from Amazon to upload, and it has the permission to access to the data. Public. Okay. And how I send you the
if you want to send the links or even files, you can use the Discord channel tutorials.
okay.
That's the easiest option, I think.
Okay, I put the right URL in the Discord dataset, Discord tutorial. I will continue, but you need to the only difference is to change sorry this for the new URL. Yeah, this is the correct folder. Okay. Yeah, I will continue, and we left here. Sorry for that, but in the next tutorial we will use mass RCNN, and that dataset is for this part. I'm sorry for that. Okay, we are here in the unit create, and we finished to create the contraction path, and we need to create the expansion path. This part is the bottom part of the U when we pass to the expansion path. And like I said before, the right side is the same convolutional path, but in the different direction. Here we need to expand our data. And now to run the output, and finally create the model. The model is summarized here. And we can check. We have the contraction path from the bottom to here. We start the expansion path in the same size to the finally output. And we have the best approach to the same size of our image and the 3 channels, but with the segmentation mask. We need to split our dataset in testing and validation. And we have, because we have a little data, this is a dimension of our different datasets. Only because this is the goal of this tutorial is only present the architecture. You can work with your own data, and maybe in that scenario, and in that scenario, you need to increase the batch of size and also the number of epochs that you use to train your model. We configure our data, data training, deep learning training, and we start the training. This take a little because we have a GPU support, but only one GPU, and I think it's not a big one. And you start to train. Like I said before, this is this tutorial from the scope of the hyperparameters of the tanning, for example, the network, or use a different validation function or something like that is out of the scope of the tutorial. And obviously you can check for different activation functions or similar. But I only want to present the unit for the segmentation task to enter the second part of the tutorial that will use instance segmentation that is more powerful tool for perform the segmentation task. And we are finished our training. Obviously, we show the training and validation loss. It's very optimistic result, but maybe it's overfitting because we have a little data, and we need to we plot the model to more visual representation, and we see the path to the constraint and the expansion path.
Humberto, there is a question from one of your attendees, and it was wondering how did you build the ground truth images?
Yes, this is a very good question because it's the one of the main challenge to train a segmentation model is to create the mask. In this case, I will use the second part of the tutorial because this is part of a work that we present in astronomy and computing, and we implementate this model. I will talk in deep in the next stage part of the tutorial, but we use our implementation of mask RNCNN to create the mask. But you can use a different tools for computer vision and also things like that. But in this case, we use the ground truth using this architecture. And this is the output of the model. Only we create a code that for the creation of the unit data set only take the segmentation mask, not the bounding box and not the classification, and we use to create the data set. Okay, and we need to displace the sorry, I don't create here. Finally, we find the training of our model, and we need to test our network with the test datasets. It's the same dataset, but only the part for validation is. And we can show the results here. It's not impressive result because obviously only trained with 10 epochs, but you can see that this is the ground truth, and this start to take the form of the segmentation. Obviously, if I training the model with more epoch and more the more batch size, I will receive a better result. But this is only for the presentation of the unit, how to start with the contraction path and the expansion path, and how what is the form of the data sets. The goal of this part of the tutorial is to show the basis of this approach. Obviously, here using a unit, there is a work performed, but I think the people from Carthage to hear this work, Morpheus. This is an excellent work using UNet to perform semantic segmentation and also classification. If you want to check a very good work to use it, UNet applied to morphological segmentation of galaxy, I strongly recommend to read this work. But the next part of the tutorial is focused in this. This is the more powerful deep learning tool applied to semantic segmentation, object detection, and instance segmentation. That is, say that I will segment this image and also that galaxy, but I will have a different identification for different instance of that class. This is a more powerful tool, and we start to show it in this part of the tutorial.
Umberto, there is a question about some people getting resource exhausted error when training the model. Have you encountered something like that? And what could somebody do in that case?
I think that maybe is for the GPU support. Remember to perform this change runtime type. We need to check that we have the GPU support in our Colab network, because that error is out of resources. Okay, this is the main part of the tutorial. I will talk more of this model, because I think that is a more powerful tool to perform segmentation tasks and also object localization, that is this bounding box over an object in an image, and also the instant the different to identify that is a certain pixel belongs to, for example, a galaxy. I think that this model need to have more application in astronomy. Well, the MAX RCNN is a state of the art of the region-based convolutional neural networks. The goal of RCNN family architecture is to solve the problem of object localization. This is the starting point. There is 4 architecture in this family before the MAX RCNN. The first one is RCNN, the second is fast RCNN, and finally faster RCNN. because to perform this task is a very computed expensive, and because of that, the creator of this model work in the acceleration of the acceleration and also the accuracy to perform the object localization. To achieve this purpose, broadly speaking, the process is divided into generate the region of interest or the proposal and classify these ROIs. In the particular, finding the ROI present a highly computational complexity. In order to deal with this complexity and solve the problem, a series of architecture based on RCSN has been presented, like I said before. But the last one, like I said before, is the state of the art of this model is mass RCNN. And like we see in this diagram, the max RCNN, there is two stage in this architecture. The first is generate the proposals and about the region where may be an object based on the input of the image, and that is the region of interest. The second is predict the class of the object, that object, and refines the bounding box and generate a mask in a pixel level of the object based on the first stage proposal. Both stages are connected to the backbone structure. Where is the backbone? It is a very important part of the architecture, Max RCNN architecture, and the backbone also is the first part of this architecture. It's a pre-trained convolutional neural network on an image classification task. For example, BGG, ResNet, the state of the art of classification using convolutional neural network. And it is called, this network is called the backbone because it's the word said is the backbone of the model, and it's the responsible to generate the space of feature or the feature map on the model. Here we can see the feature map of the architecture. Like, you know, the network, the convolutional neural network for classification task has a final layer, like the similar to UNet, that, not the similar to UNet, the similar scope to take off the dense layer to perform the classification. In this case, we will remove the classification layer, the final layer, because we only need this network as a feature map generator. In this case, this is how what is the output of the model and the input for the next stage of the model. For example, we have this input, and this is the feature map that the convolutional neural network in the backbone generates, and it's the input of the next stage of the model. For example, here for the tutorial, we will use a ResNet, the residual deep neural network, ResNet, with 101 layers, and is pre-trained with we will use a transfer learning the weights are for the work I talked before, that is pre-trained to classify and segmentate morphologically weight the galaxy. For example, here, the feature map acts as input for the following stage of the model. In the feature, it shows the feature map that is at the backbone. It can be seen how different layers are sensitive after training with our dataset to astronomical objects in a different spatial scale. For example, we see this is a little galaxy or little stars here, and the main source in the middle. And here, this is we can summarize all the process or the stage in the mass RCNN architecture. It shows by step procedure followed by the entire model being applied to a SDSS image. This is the output of the backbone. And next, we need to start with the RPNM. The RPNM is the next touch in the model. It's a region proposal network. RPN is a lightweight, fully convolutional neural network that operates as binary classifier. The process consists of running a small spatial window on the feature map generated by the backbone of image to generate a set of potential regions called region of interest. These proposed regions or proposals have different size because they depend on the size of the spatial slicing window used to generate them. The size of such slice windows defined an anchor box. This is this is part of the configuration that we perform below to the notebook. And the network has many anchor boxes that have pre-trained location and scales relative to the image. This is important because it depends on the problem we need to solve with this model. The size of the particular anchor boxes are closely related to the nature of the problem. In particular, for our work or for our tutorial, we will utilize anchor of size 4, 8, 16, 32, and 128 pixels. After the prediction or the boxes for the prediction are generated, in this case, we are talking about galaxies. And any model that aims to classify galaxies should consider they are different sizes because of, for instance, a Milky Way galaxy is 100,000 light years of diameter, approximately. And for other hand, galaxies such as M100 are approximately 52 million light years of diameter. Furthermore, galaxies will exceed a particular angular size according to their distance. Following this rationality, the size of the anchor that we use consider the size of the input of the image and the variety of the size of the galaxy, because you know they are no astronomically speaking, only in the scope computer vision image, we have galaxies object the size of the half of the image, and we have galaxies that are small compared with that. Because of that, we need to parameterize these different slicing windows to find the small objects and also the biggest one. The size answer that we use consider the size of the input and the image also, and the variety of the size of the galaxy that we can find in such an image. In particular, we chose a small answer considering the small size of the object in our sample dataset. The pixel scale is 260 for 260 is the size of the input image that you find in the dataset. Well, after generates here after generate the boxes, the RPN generate answer are 3 different scales and 3 different aspect ratios. Each of these answer has a objectiveness-based score of 2 classes, object or not object. Finally, non-maximum suppression, NMS, is applied to the answer in order to remove the boxes that have not overlapped, because we want to the region with more overlapping. This is the goal. In practice, but this value is calculated using intersection over union metric, and the boxes that not reach a predefined threshold are removed. Intersection over union is a very common metrics in this kind of architecture, and make sure the overlap between 2 boundaries in EOU is the relation between the box that represent the correct position of an object, the ground truth, and another box that represent the prediction of the model for that part of the image. And this is the part that I are talking in this moment. And next, the RPN proposal that passed the binary classification process, object or not object, go to the next stage with the name of ROI, or region of interest. After applying no max suppression, there is a fewer answer than the number of candidates. This filter answer are renamed as a region of interest. And this ROIs, or region of interest, go to 2 processes called ROI classification and bounding box regressor. The result of this process generate 2 outputs for each ROI: the class of the object and the bounding box for that object. The classifier, unlike to the RPM, incorporates the real class that the object belongs. In this case, whether it's an elliptical or a spiral galaxy. In the case of the bounding box regressor, it's necessary to make a size adjustment because the different size of the boxes generated by the RMPM. This is the 2 states I talk right now. And also, the pixel level segmentation stage require much more fine-grained alignment with the bounding box. Therefore, it's necessary to obtain the fixed size of the boxes first. For this purpose, the model incorporates the stage called ROI alignment layer. The ROI alignment mechanism is based on cropping a part of the original feature map selected, bounding box, and resizing into a fixed size. Here. And finally, of a very extensive process is indicated before, a unique element of the MATS RCNN architecture for the object of this task is the ability to segment and also identify different instance of the particular class. The mask is generated by a full convolutional neural network receiving the input, the ROI selected by the ROI classifier. In other words, all the region that contain objects of the classes that exceed the minimum parametrization accuracy, the threshold, and with a bounding box, of the defined size. This is the combination of these two parts of the model. One important aspect to consider for this model is the particularly that the astronomical sources do not exhibit sharp edgeheads. In this sense, the masks are cheap to the pixel level and is represented at the floating numbers, achieving this more precision to do whether or not pixels belong to the classified object. This is a relevant aspect for the automatical segmentation of astronomical sources generated by the model. The final result is verified for the classification, location, and segmentation of the in this case 3 galaxies. This process occurs with a single automatical pipeline based on a one deep learning model. This is the final statement for the max RCNN, because this architecture in one pipeline perform classification, object localization, and semantic segmentation. Because of that, I say that is one of the most powerful approaches to apply semantic segmentation or morphological classification of galaxies, for example. In the tutorial itself, the first thing we need to do is to define a particularly version of TensorFlow and Keras. We need to run this and install the requirements to setting up our environment.
Umberto, there is a question about
Okay.
how well does this model deal with overlapping or partially connected sources?
Oh, okay. Today the question are the better one because that is like I said before, we have a work published, but that is that are working right now because in fact the case to show the result of our model, I only for I think that is not okay. In the final stage of the tutorial, the test case is to show the overlapping galaxy, but that is a more hard problem because it's very difficult to separate the galaxy. But we have a decent result right now. But I think that the best approach is also training the network and with this overlapping. We have the galaxy separate and also training with the overlapping. But it's a very good question. That okay, I will continue because I will talk about that problem in the final part of the tutorial. Okay, in the first part of the tutorial, we use mounting our Google Drive, but in this part we use a different approach because in this case we programmatically modify the sharing settings of the data. We need to, we programmatically create data, and Colab don't allow us perform that. Because of that, we use a traditional Linux approach to use Colab, because I don't know if you know, but Colab run over Ubuntu Linux. Because of that, we can use all the traditional Linux commands to perform or use in this tutorial. First, we go to the root, or our root folder, not the root for the Colab. And in here, we need to create a folder called ADAS. And we need to clone, in this case, our implementation of the Max RNCNN. Okay. And now we verify that the repository was cloned correctly. And it's okay. We have the model here. And we need to import the libraries. All this is to set the root directory. We import our libraries. The principal are this one, the RCNN, the mass implementation. We check that we have the correct version of the Keras and TensorFlow. You need to have the same output here, because the first part is to install this particular version. This is only for not showing the warning. We need this important install or import JSON, because the dataset for mass is a different approach than the unit, and we will use a JSON file, and this is only for plotting the results. Like I said before, the data set is different to the unit, because we have separate the folder for training data and validation data. In both folders, we have image, JPH image, with 3 channels with any annotation, because the annotation is present in a JSON format, in a JSON file, in the COCO format. Because one of the considerations to use a convolutional neural networks in general is the need for training data set of the image able to satisfy the following 3 requirements. The first is the object in the data set have to contain a label indicating the class to which each object belongs. In this case, is a elliptical galaxy or a spiral galaxy. Second, the convolutional neural network require also to be equally represented in the dataset. And say it in other words, we need to have balanced classes. Ideally, have the same number of example. This is all another problem or different techniques to achieve this problem. But in this case, we select a little number the equal number of the spiral galaxy and the elliptical galaxy. This last requirement implies that the dataset needs to contain many images, usually several thousands of that. In the case of max RCNN, this is also necessary to incorporate an additional element of the mask. This last element is a key factor for the architecture because it provides the segmentation shape and implicitly the location of the objects. For do that, we use a tool called or a software called BGG for the annotation image, and also a code using a scikit-learn to generate a segmentation to train our model. And all this information is put in this file in via region data JSON. Now we need to clone, I hope, the correct dataset in our folder. We need to uncompress the data. This is okay. And this is the file that contains the segmentation mask and the label and all the information that the model needs. For example, here, this is the name of the image, and this is, for example, we say that the mask is a polygon, and all these are the points that define this mask. And the object is a spiral galaxy, the size of the object, and so on. If we have, for example, more galaxies in the same image, we have one definition for one object in one image. We need to define the path to this data, and we need to also for the data is that we will utilize in this tutorial. We use the labels is from the Galaxy Zoo, and the image are from SDSS, access to through the Sky Server web service. For each labeled object, we download an HGPA image center of the coordinates. And this is important, the weights, because we don't start from a black network or an empty network. Like I say in the first stage of the tutorial, we start with a pre-training convolutional neural network, in this case ResNet, and the weight of this tutorial, we will use the weight of a pre-training network that we use in this work here. If you want to check it, I need to create the model. If you search in the web for other tutorials to the mass RCNN, all start from the COCO dataset. It is a very broadly used or know in deep learning applied to this task. But here we start with a network training to perform classification, galaxy morphological classification. We need to download the data sets, the weight of the network. Okay. and we need to define the path to the model and the weights. Here is the configuration to the network that has a lot of hyperparameters. The first, we need to define the number of GPU and the number of image that we pass for any GPU we have available. In this case, we have only GPU. Like I said before, we have a ResNet with 101 layers. We can also use a ResNet for 16 layers, or maybe use a BGG or another convolutional neural network using to classify images. And we have two classes because we have a spiral galaxy and elliptical galaxy. And also we need to incorporate a third class that is the background. Only is always present in this approach. This is a threshold that defines the minimum detection content. For example, this is if in the training we find a galaxy or the detection with accuracy of 20% are excluded. Obviously, in the detection stage, we increase this threshold to 90%. But in this case, we use for training that parameters. The size of the image and the resize mode is the crop that we see in the more advanced in the tutorial. We define the RPM anchor that I'll talk in the first stage of the tutorial. This is a very good approach, similar to the if you are working with, for example, tabular data and deep learning, you know you need to normalize that data, and in the way you don't have points that escaped for the normal distribution. Similar approach is to have the mean of the pixels, and we define the length of the size of the data in the training and the data for validation, and the number of inputs and the number of validation steps. This is a very small because this is the real approach is following that formula. Obviously, you want to use for your future work, if you want to use this architecture, because it is a fully operational architecture. If you change the data set to another data set, the network is continually working for your own project. You want to change these parameters, for example. And in this model, we use a ReLU, but like you know, right now are more advanced, maybe activation function like leaky ReLU, for example, or another in the family of ReLU activation. You can use that also. And this is an important parameter for performing or speed the training, but we see in the next part of the tutorial. We set the configuration and it's worked correctly. Here's the configuration. This is for the showing the results. This is only for the notebook displays preference to define the size of the image that we show in the later part of the tutorial. Also, we have to define a data loader. In this case, we see we have one for spiral galaxy, two for elliptical galaxy, and here are commented tag before, like you know, and in Galaxy Zoo there is a uncertain, but it's only to show that we can use many classes here. It's not a binary classifier, max RCNN. We can use any number of classes if we want. Here we define the subset, train and validation, the file that contains the segmentation mask and the label of the data. And here is the when we extract that data and put in the annotation format for the data. And this is part of the loading. You can read any details you want, but it is to load the mask from the JSON format. And now we need to load the training dataset and also load the validation dataset. Here we will show how the data is presented. This is important. For example, here we have a galaxy that we see the mask, but we see has incorporated another galaxy, and here is failing totally because not had the shape of the galaxy. But it's important because we use for this to prepare the mask traditional approach using scikit-learn, for example, because something like that. But the model, the output in the model is very very best in to generate the segmentation mask that we see in the tutorial, that the traditional method that we use to show to prepare the data sets. This is the ground truth, for example. And the bounding box, here, this is only here is I will show you the part of the how we work in the practice, the hyperparameters of the network. One is the bounding box. This is the ground truth in this case, and later that using the bounding box coordinates provided by the source dataset, we compute the bounding boxes from the mask instead. For example, with this, I say that in the JSON there is a no field that say bounding box. We compute the mask over from the mask information. This is allows to handle bounding box consistently, regardless to the source dataset, and also make it easier to resize, rotate, or crop image because we simply generate the bounding box from the update mask rather than the computing bounding box transformation for each type of image transformation or data augmentation. This is very important because we do it in line, and depend only the mask. We don't need to recompute the bounding box and incorporate new information. And another important part, like I showing here, that is minimask here. This is solely for the speeding up the training. It's not a hyperparameter that depends on the theoretical model behind max RCNN. It's only for speeding up the model. And minimask. Minimask is a instance binary mask. We can get large when training higher, higher. For example, if we the mass, the binary mass that is presented in the JSON file, for example, if we have an image for more biggest image for 1024 for 1024 image, then the mass of a single instance require a 1 megabyte of memory for one image. If an image has a 1000 instance, then that we need to deal with 1000 megabytes for only one mass. To provide speeds, for example, here is the original mass present in the JSON file, and minimass is like what you see is similar, but is we optimize this with storage the mass pixels that are inside the object bounding box, not outside. For example, here for the mass, this is not present in the mass or the NumPy matrix that has the value for the mass rated that the mass are the full image, because all the points that are not in the bounding box are 0 because there is any object of that, and the most objects are small compared with the image size, and so we have a space that is not storing a lot of 0 around the objects. We resize the mass to a smaller size for object, that the larger that the selected size, we lose a bit of accuracy, obviously, but most object annotations are not very accuracy to start. So this loss is negatively for most practical purpose. And for example, the final layer mass after to this mini mass approach is very similar to the original. For the human, we need to maybe to make zoom to find difference, but this increase the speed of the inference and the training model, and I don't know what is the numbers exactly, but it's very powerful approach to increase the speed of the model. Well, finally, we need to create the model, and we read the folder where is the model, the weights to the model. Here we create the network in the training mode, because also have the inference mode that we see in here in the detection. And we will start training the network, but not including that only focus and training, and here we'll start training the backbone, but no this layer, only using transfer learning to the capacity to generate the bounding box. All the other parts are training again. And here, this is because we read only the backbone capacity. We exclude the other part of the model to the generate the bounding box, the mass, and so on. And it's okay. And this is another important aspect to consider when you train this kind of model, because not always has the amount of data that you need to train this kind of model. Because of that, we use data augmentation. The training and validation data set are able to satisfy the needs of the problem in terms of values, volumes, and the balanced representation of the examples for each class in this case, because we select that. As indicate the use of transfer learning based on the backbone of the network and the training strategy, we can provide a base knowledge to train the model. But also, as indicated in some works, the use of data augmentation helps to improve the ability to generalize the model. In data augmentation process, we will use ImageUt library. It has around 100 possible imaging augmenters and augmentation techniques, like you see here. These data augmentation techniques include affine transformation, perspective transformation, construct change, Gaussian noise, dropout of regions, hue saturation changes, cropping and padding, and so on. But in this case, to the galaxy morphological classification problem, not all the augmentation techniques have a scientific relevance for the characteristic of the astronomical image. For example, maybe this technique don't have a pertinent or scientific correlation with the problem. Because of that, we need to select the correct the correct data augmentation pipeline applied to the dataset. In this case, we use 4 techniques. Or this pipeline consists in a sequence of 4 techniques: flip flip for one side, flip out, one off. In this case, has a different 3 options. For one image, the augmentation techniques select one, and for other image, select another to rotate the image, because elliptical galaxy is presented in vertical position. If we rotate, it remains a spiral galaxy, and so on. Is intended to always perform exactly in one of the techniques that the group in this block, like I said before. And finally, we have the arithmetic technique called alt element wise, which aims to create new image by adding a slightly different pixel in the neighborhood. All of this is to create a new image from the original data sets. And here we have the training, and we have the a different parameters we need to configure. One important is the layers. We can train all the layers. That is the case, to fine tuning, to more has for example a learning rate more intense in the first layers or in the last layers of the model, because, like you know, in deep learning, the first layers of the model are dedicated to find the borders, or not the more advanced features, but the last layers are focused in that. For example, the difference between the final elliptical or the form. So, excuse me. And we, in this case, we chose a traditional learning rate, a very template learning rate, and also we perform a fine tuning over all the data. But in this case, I will don't run it. If you want, run and wait for 1 hour or 2 hours to finally to training the model. But the correct you need to see eventually is here when start the training. I will not do that in this moment because the tutorial is finished. But we have the when you the training finish, you need to storage your model or the weight of your model in that way. And here it's the same. We start to reading finally. This is the part of training and the part of the detection part. You need to are the same. We start to the folder, but in this case, like I know not restart the environment is not necessary. I go to directly to the inference mode. In this case, we need to create an inference stage of the model different to the training mode. In this case, we define 1 GPU, 1 image per GPU, and the threshold of the detection confidence. That is the model. Don't focus in any galaxy that the accuracy is lower than the 90%. And we configure it. And now we are running, sorry, lower the weight, this weight, and it's okay. This is the same. All this is you run this and you say, oh, I don't wait for finish. I will restart the kernel. We run the same configuration to lower the library. Because of that, I put here if you want to restart from here. Maybe this is another notebook if you want, but this is all the steps you need to perform if you want to detect image. No, it's not necessary to perform all the stage upper from here. Is here. I need to read the validation dataset. And this is for the visualization. Import datetime. Select one image for the validation dataset. And this is the ground truth. This is that we present to the network. For example, is this model, this image is used for training, but is not part of the training dataset. It's part of the validation dataset. And the goal, obviously, is to do better than this. We need to define the name of the model. And we perform the detection. This take a little. Maybe if you later you load the notebook and you run in Amazon Web Services, or maybe in your computer with a GPU, this will run very fast. But here it's running slow because the computer support we have, but eventually it will finish. I need to wait for a little. And here, this is finally the result of the model. And we see, in this case, had a segmentation. And finally, this is, if you want to perform this for the final preparation of your data, for example, you create your model to select to find, for example, pulsars or galaxy with a special characteristic, and you need to present your result to a reviewer. You need to calculate the final accuracy or results, and the map is that you use. Here you need to put the size of all your data in validation and run it and obtain that result and put in your paper. And this is the finish of the tutorial. This it will finish in a few moments, and we see Patty set a toy example because I only put 10 images to calculate the map and to compute the precision of the model. But this is all I wanted to show you today. I see there is a question. Okay, I see there's a question. Yes, it's because this model depend on NVIDIA support.
So the question was whether you can run this model on your laptop. And actually, I had a similar question myself. Suppose I wanted to run this type of models on my image data or whatever locally. And what would be your suggestion? I mean, I guess a laptop will not quite be enough. So would you suggest setting up a server with a GPU or more, maybe than one GPU?
Yes, but maybe a laptop is enough, but depends what you have in the laptop. For example, I can train in the model in my laptop because I have a Mac, and I don't have a NVIDIA GPU support. Because of that, I use Amazon Web Service, and I upload my data similar to the workshop here to S3, and in fact, I will show you where I training my models. And this is the AC2 machines for deep learning, and you can choose in this case the number of the GPU you want in your model, but it depends on the size of your data. For example, for training the model that is in the paper, we for only one version of our network takes 5 hours to train all the data, but we use this network Is this has 8 GPUs, and obviously this is stopped because Amazon is you pay for the use in Amazon. In this case, I always is the time, but when I want to train the model, I start the machine and connect to the machine and training my model.
Wow, 8 GPUs.
Yeah.
That's quite something. Look, there are also two other questions. Have you tried with more efficient networks like MobileNet version 2 or EfficientNet models?
Yes, in the fact, this is a spoiler because I have a poster in others that in that case to increase the speed of the inference we use a BGE, but we compress the size of the nodes of the neurons, pardon. Because one of the principal complexity of the network is the number of parameters need to calculate in any stage. Because of that, we use a tensor decomposition method. This is similar to PCA or SVD or in general matrix factorization, but apply to a more general or more dimensional space. And we achieve an increase of speed on 2%, or we reduce to the half the time to perform the inference and the training, but using that technique. But obviously you can change the backbone for any classification convolutional network, neural network that only you need to the network has the ability to create the feature map.
Okay, wow. There are a few more comments and questions. One was, suppose you don't have access to a GPU, maybe because you, well, for whatever the reason. Will the model run at all on something without a GPU? Or does it need, in this particular case, a GPU, to run at all?
The answer has two answers. For training, you need a GPU. That, in fact, is the reason because we don't have deep learning in the past. Because in the past, because I don't know if you know, but the deep learning of the convolutional neural network are invented in the 80s, but we don't use that models because we don't have the computational support to perform, for example, the convolution. Because of that, we need to GPU for training. But for inference, you can use a CPU because you don't lower your weights and you can run in a CPU.
Okay, fantastic. One more question. How much data was used to train the model? And what were the critical elements in the data set to get good results?
Yeah, the data sets that we use for the task in the paper, we used 24,000 of images. There is many aspects that we incorporate in that work. For example, we only use the brightest galaxies in the image, and we center the image. We use like I say as a sticker because we have only galaxy in the center, but the network works in a big plane and find the galaxy. And but if you want to speak in general terms to prepare to data set for deep learning, you need to take care of the number of images, and you need to have a balance in the class. For example, you have 10 elliptical galaxies, you need to 10 uh, spiral galaxies, but there is a technique, for example, that you have punish the class with more examples, and you can increase artificially the weights of the class that is less represented, for example. This is one approach also. But it's very important to the class are equally represented, because if you don't have that, the model learn to more a lot of more in the fact to the class are more dominant. And there is and other aspects like in this case we want to improve is when we generate the ground truth, like I select the worst case because I want to see that the traditional techniques, for example, to automatically generate the ground truth, they are not very accurate. And because of that, in many cases in deep learning, the annotation is performed by humans using a, a web service tool. You upload your image and you manually generate the mask. Because of that, we want to use a unit to generate the mask and then train the mask RCNN.
Okay, fantastic. So could this tool be used to identify H2 region in the individual galaxies, even if they are indeed overlapping, for instance? Christoph is asking.
Yeah, that is the question that another person asked me before. But in this moment, we don't have the ability to perform the overlapping segmentation with accuracy in this moment. But we applying to the galaxy morphological segmentation. But in the real problems day-to-day classification, for example, I have a car here, I have a car before, that is solved. But what is the main difference? Because in the real world are shapes, for example, and the galaxy are very soft, and that is one of the biggest problem to achieve that overlapping classification. We are working in some approaches to achieve that, but in this moment it's an open problem.
Okay, some more question. Is there a possibility to add another regression head to the network? For example, for predicting the viewing angle of a galaxy? And is that something that can be done?
I don't try that. This is a very interesting idea, but in this moment I don't work on that. But you always remember that we can use a model, a standalone model, for example, like here. But always you can create an ensemble of models, for example, we want to do now. For example, use UNet to create the input to the max RCNN. Maybe you can add a stage between the feature map and the right alignment, and put another network that performs that task that you are commented before the classification and bounding box and the segmentation. I think that maybe work. very optimistically. But I think there you go.
And another question. The algorithm is affected heavily by noise and resolution.
Yeah, that is a very good question, because I don't refer that in my talk, but in generally the convolutional neural approach to the instance segmentation of object localization is very responsive to support the different, for example, in noises. In the fact, in the paper, we artificially incorporate a Gaussian noise to the image systematically, and in the fact, and there was an point that is ridiculous, but the network continually identified the galaxy. But obviously the accuracy is slowing, but for noise it's very don't affect too much, but the size is a different kind of problem. Because if you remember the first part of the talk, I talked a lot about the size of the anchor. And because of that, if we have a very big, say another word, you need to train your model in taking in the mind what will be the final application of that model that you are training. If you train in the model to find galaxies in a certain sizes, you put that sizes in the model, because if you don't put, it's very probably that the network don't see, for example, the biggest one galaxy, for example, that cover all the image, or the little ones. That is, I think, the answer to that question.
Awesome. Well, Humberto, thank you so much for your tutorial. The next one will start in exactly 5 minutes. We know that preparing these tutorials is a lot of work, and we are really grateful that you spent the time and you work hard to deliver a great tutorial. And we are all very, very grateful. I found it very interesting. I learned a lot from this tutorial as well. I also learned that I have to buy some GPUs, but okay, that's life. And so we would really like to thank you again. And folks, for everybody else, the next one, Peter's tutorial starts in 5 minutes. You can keep discussing with Humberto on Discord, and you can use this 4 or 5 minutes to get another coffee, or eat something, or whatever, run to the bathroom, whatever, and then we will start with Peter. Humberto, thank you so much. Thank you.
Thank you for the invitation, also.
All right, folks, we start in a few minutes with Peter. And again, Humberto, thank you so much again. Peter, I see you already in there. Okay, you're muted, but...
That's intentional. Hopefully you can hear me now.
We can hear you and see you perfectly. So just a few minutes, and let's have people take a break. I want to mention just, folks, that we are amazed by the incredible attendance to these tutorials. We are, getting close to 100 people attending between Zoom and YouTube. And this is just for the live portion. And, we'll see how many people watch the YouTube streams. Peter, also in your case, we are getting close to 100 people. So pretty cool attendance. So see you in just a couple of minutes. We'll start and we'll start with Peter's tutorial.
And can you see a title slide for my screen share now?
Yep.
Great.
It's perfect. Okay, Peter. Well, I'll just briefly introduce your tutorial. We are lucky to have here Peter. He's going to tell us about exploring and visualizing data on the sky with Jupyter and PyWWT. Warm welcome for Peter. It's the third tutorial of ADAS 2020. As I mentioned, we are getting a fantastic attendance to these tutorials, and Peter is no exception. We are close to 100 people, and it might be a record for ADAS actually. So I'm looking forward to your tutorial, Peter. You can start whenever you want. I bet, I guess people had enough time to get a little bit of a coffee and everything in this 5 minutes. So thank you again for giving the tutorial.
Thank you, and good morning, everybody. It's fairly early here in the U.S., and it's been a busy week. So it might take me a few minutes to get up and running here. But I'm glad to be giving this tutorial and excited to be. So it's a little bit new doing it in the virtual format, but hopefully we've got something set up that'll be informative and easy to follow along with. So yeah, what I want to talk about for the next couple hours is data visualization and data exploration in Jupyter, using specifically this PyWWT Worldwide Telescope software that I'm going to talk about. But one of the ideas that I want to sort of reflect on is the broader applications of what will be going on here, because as many folks involved with this conference know, data sets are getting bigger. They're living on servers and archives that aren't local, and the question of how you visualize data that live in some server on the other side of the world is really challenging, and it's what a lot of our existing software is not able to handle. Not only can you not download a FITS file from across the world easily, if it happens to be 10 gigabytes, it might not fit in the memory of your device. And as we've seen with the science platform concept, which seems to be spreading around, the way that we're going to be visualizing data in this new world is through the web browser, and specifically through Jupyter for pretty much every science platform that I'm aware of. And so this is actually a really big change, because almost all of our existing visualization tools are not built for this paradigm. And so it's going to be a time of turnover as we get new visualization tools that all, the thing they're going to have in common is that they're going to operate through the web browser. So to get started, the bulk of what this is going to do is going to work through some notebooks that are hosted in the cloud on mybinder.org. And so if you go to this URL, small.cat/fog, it will be a short link that will start loading a Binder notebook on mybinder.org. It will eventually pop open a Jupyter Lab interface that will look like this, which should pop up in a second or two because there's some lag in the screen sharing. And so these are just running in a VM somewhere, and you can just do whatever, and you can come back to them whenever, except so this URL shortener that I've used here. These are the reason that it's easy to pronounce is because it's temporary. So if you come back in a few days, small.cat/fog might take you somewhere else and might take you somewhere you don't want to go. So a permanent link that will launch these cloud-based notebooks is the one down here, bit.ly/pywwt-notebooks. So that one will always work. This small.cat/fog one is temporary. And so this should run in any modern web browser, and it will take the notebook probably a minute or two to spin up. Not too long, hopefully, but you should open that now, and then I'll give a little bit more introduction, and then by the time that's done, hopefully it will take you to this screen. And one thing to keep in mind with running things in the cloud is this is just a web page, web app running in a web browser, so feel free to fool around and try things, and the worst that can happen is you have to hit reload to restart it. Jupyter is stateful, so there's some things that change, but I think that's one thing that's different from a local software installation that you kind of have to get used to is there's a lot more ability to just kind of hit the reset button and start again if you try something that doesn't work out. So to continue with the introduction, as I've said before, so we're going to be exploring data on the sky in particular using Jupyter and Python. So the key tool that I'll be demonstrating is a Python package called PyWWT, which is part of the AAS Worldwide Telescope project, which is I'm the director of that project. My employment split between the AAS, the American Astronomical Society, and the Center for Astrophysics at Harvard. So I'm going to assume a basic familiarity with Python and Jupyter and how you use the Jupyter and Jupyter Lab interface. But the way these notebooks will work is there isn't going to be any live coding. You can basically just run through the cells, hit enter, control enter or shift enter or option enter, depending on your platform, and just execute them all. So don't worry about having to, solve coding problems on the fly here. We try to support browsers widely. Google Chrome is recommended. And one other piece of information is that the way that Worldwide Telescope works is it's kind of like a game rendering engine where it's continuously redrawing because it actually has an internal clock. And what we're showing, we'll see some of that. But it actually, the Worldwide Telescope software contains a model of the solar system that is scientifically accurate and progresses with time. And so so as you leave it running, you might, in principle, if you set it up where you can see Jupiter on the sky, you could see it move over time. So anyway, it will get a CPU running. And so so it will be more actively using your power than a passive viewer. Second set of points. So I've done a few virtual tutorials like this before, and I feel like the interaction is often the best part of these things, and that's definitely challenging the virtual format. So I will be looking at the Discord and trying to keep an eye on these things, but from experience, I can say that that's definitely challenging to do while also talking and working through things at the same time. So for the hosts, if feel free to interrupt me if there's a question that I haven't noticed or something like that. I think the sooner I can answer questions, the better.
Cool.
and I'll do my best. But it is true that, just all have to be sort of, I can't see all of your faces and I can't see whether anyone is confused or not. So I'll mostly be working through this. So please do interrupt me if there's a question, and hopefully there won't be any technical difficulties with as many people as we've got. I'm not really sure how to work through those if those arise. But do know that, again, you can pull up these notebooks at any time. And certainly after this tutorial is over, you are free to ping me and find me on the Discord or email or Twitter or whatever else. And then I can give you some more personalized attention. So I do see a question about putting the URLs on the Q&A. Is one of the organizers able to copy paste those in?
Yes, I can definitely do that. Don't worry, Peter. We also have a question hand raised from Sebastian. So I will just allow him to talk and ask you the question directly to you.
Great.
So Sebastian, you can unmute. If we cannot hear you, Sebastian, maybe you can write the question in.
Yeah.
Oh, okay.
Heard something there. All right, well, maybe I'll keep on going, and yeah, if we can type in the question somewhere, then we can answer it when that's ready. And yeah, finally, so I encourage you to try and follow along with what I'm doing in my Jupyter notebooks. If you pull open your own copy, I think that will be helpful. But if you don't, then again, you can go back and do it later, or just watch and see what we demonstrated. Oh, and one other thing I should say is a lot of the strength of PyWWT is that it's interactive, and you can, there's sort of a spectrum of, are you exploring your data and kind of getting a sense of what's going on, or are you preparing a polished visualization to make a specific point that might appear in a publication? And I'm focusing more on this exploratory side, where there's often a lot of interactive zooming in and figuring out what you're interested in. In order to make everything legible, I've shared my screen in the zoom mode without the video enhancement, because that degrades the resolution a lot, which has the trade-off that the interactions will be quite choppy. So it won't look very great, and it might be a little bit hard to track what's going on. I'll try not to drag things too quickly. Hopefully in your own web browser, things will be much smoother if you're interacting with visualizations yourself, and it will be you'll get a better sense of what the experience should be like. But just be forewarned that a lot of the interactions will look pretty bad, but that's because of Zoom, not because of the underlying software. To set the stage a little bit more, so this is what I'm primarily going to be showcasing is part of the AAS Worldwide Telescope software system, which you may have heard about. It's been around for a while. My summary of it is it's a tool for showcasing astronomical data and knowledge, which tries to get to a point that Worldwide Telescope is a visualization engine. It's got this model of the solar system built in. It's got a huge set of data assets, and you can use that for research. You can use that for education, but it's really, what it is about is data and telling stories about that data, which helps us understand what's going on. It's a real system of software. So you might think of Worldwide Telescope as being this Windows application, and that's how it started in Microsoft back, more than 10 years ago at this point. But the core rendering engine that powers the Windows app has been extracted, and it's now this reusable JavaScript TypeScript library that powers a variety of applications, including this Python Jupyter interface. And so because of that, it's software that you can use for education. You can use it for research. You can use it for public outreach and just sharing data in a way that people can enjoy. So that means it can be a lot of different things to a lot of different people, but regardless of which kind of facet we're thinking about, we're free, we're open source, we're striving to be open development and welcoming. And one thing that has really evolved with the project over the past year in particular is a lot of our kind of open source way of doing things, of having everything running on GitHub with a bunch of continuous integration and continuous deployment, has gotten a lot better than it used to be. So especially this JavaScript library has gotten a lot better. We've wrapped it in TypeScript wrappers, which make it, if you use more modern JavaScript frameworks, that helps a lot of things. And so I think it's in a place where people can really build some exciting apps with it. So for today, hopefully your Binder Hub notebooks are started up. I just want to demonstrate a few things about looking at the different kinds of data visualization that we can do, specifically tabular data, so catalogs, imagery, and also, as I kind of alluded to before, showing how the fact that we're doing things in Jupyter, like what's really important there is it's code that runs in the web browser, and web browsers are everywhere now. You've got a web browser in your phone, you've got a web browser in the dashboard of your Tesla. And so that means that if you have code that runs in the browser, it can run in a lot of cool places. So by now, I'll show this notebook again. Hopefully it has loaded up for you at this point. So I'll switch to a tab showing my version of this Start Here notebook. And so this is kind of an index page which has links to a few different notebooks, which I think in the default view, you should see this sort of file explorer here. And so one thing I want to emphasize is the interface that we've got here is the Jupyter Lab interface. So not a single Jupyter notebook, but this more integrated Jupyter-based research environment. And in a certain sense, I think it's a little unfortunate because the names are similar and the difference isn't really obvious all the time. But Jupyter Lab is a much more complex and sophisticated environment where you can, it's a full data analysis environment, whereas the Jupyter Notebook is kind of a document, more specific kind of thing. And what we found is that running things in Jupyter Lab, you can use Worldwide Telescope and our viewers in a single Jupyter Notebook, which might be, on its own or rendered into HTML or wherever else. But this integrated Jupyter Lab environment is where things really shine. So I think actually to show how to get started using Worldwide Telescope, we'll just start the first part of looking at tabular data. So I'm going to click on the notebook here, which is labeled Visualizing Data Tables. So we'll start with tabular data here. And if I just click on that, it should open up a new tab showing a Python notebook here. What we'll do is I'll just start, first there will be a little bit of setup to do, so I'll start with that. And again, so what I'm going to be doing here is just clicking on the Python cells and running them. Hopefully this is legible to you. My font seems pretty big right now. But again, I won't be typing any code on the fly. So we have some data tables embedded in this environment. So the first thing I'll do is run a line of code to load up one of these tables with AstroPy. And this command will just print out the first 5 rows. And we'll see what kind of, get a sense of what our data are like. So if you haven't seen this before, in AstroPy, if you load up a table and print it out, it has this built-in code to display it in a fairly nice way. And so we see the column headers here, and you can sort of get a sense of this is a table of data about exoplanets, and we've got things about like the name of the host star and the name of the planet. And if I scroll over, there's a whole bunch of information. So we've got RA and DEC, and this looks like a distance because it's measured in parsecs and things like that. So this is basically a data table of information about planets. And what I'll do now is if I move my mouse over to the corner here and click on this folder icon, that will make this left pane collapse and give me a little bit more room, which I'm going to use. So I'll do that now. And you can just make it come back by re-clicking the icon or one of the other icons in this sidebar. So to actually start visualizing, so we're going to use this PyWWT module, which is preloaded in this environment. So I'll import the name of our widget here. And the model that we have right now is that in the same way that you might plot some data with matplotlib and run a command and you get a plot in your Jupyter notebook, we'll do the same thing to create a worldwide telescope view, except that we can sort of interact with it later. And I'll show an important way to set things up that makes the environment a lot easier to use. So I've done my import here. And now if I run this command, I'll create this widget. I'll save it in a variable named WWT. And it took a second there, but it pops up as a window here. And so you can see, hopefully, a view of the galactic plane. And, you know, this is nice, but also if I click and drag, you know, this is an interactive view that we can explore around. Now, so this is an output of this Jupyter command. And if I keep on writing code, this is going to scroll off the screen, which is not a very convenient way to interact with my data. So an important thing that we can do in JupyterLab is if I move my mouse over to the left of this widget, eventually you'll see this kind of blue bar pop up. And if I right click, or if you're on a Mac, I think a control click will do it, I can get a pop-up menu that gives me a variety of options. And I'm going to click this thing called Create New View for Output. And so if I do that, it will pop open in this case. So we see the same kind of view, but now it's in a separate tab. This is a really useful thing that you can only do in JupyterLab. If you have a single Jupyter notebook, you can't do this kind of new view creation. But in the JupyterLab environment, it will. So I see a question about, will the output view automatically refresh as cells are executed? So yeah, so we'll see that. So what is a little bit of a tricky thing is once I've created this new view, this old view stops working due to some technical issues, but it's also kind of what we want anyway. So if I just single left click on this old view, that makes it go away. And then if I click and drag on this tab, the setup that I find that I like is if I drag it over to this side of my screen and wiggle it around, eventually you get this sort of blue box showing how you can rearrange the tabs. And if you drag it towards the middle right and get it to a point where you get this kind of view that you're hopefully seeing now with this vertical blue box, I'll split them, the two panes, side by side instead of top bottom. And I find that to be the best kind of framework for working on data and visualizing them at the same time. And finally, I'll drag this gutter over a little bit and even out the size. So once again, I've got this interactive WWT view right now, which right now is just showing a default map of the sky. But we'll start getting data in there and exploring the data. So the text here is just recapitulating how to do this setup. And we've got some work undergoing right now to have things be created in a slightly different way, which will make it a little bit easier so you don't have to do this right-click new view stuff. All right, so the first thing we did was we loaded up a data table, and now we've got our viewer, and now to put them together. So this WWT variable that we created is a Python variable that talks to this viewer widget. And it's the way that we get data into it or query what's going on with it. And so one of the first things I'll do is exoplanets is our variable that is this data table. And there's some built-in stuff to get the data from the table into the viewer. So if I run this line of code, you might not see much of a change, but there has been a bit of a change over here. Some dots have popped up. So the code here looks at our table and realizes that there are columns that correspond to RA and DEC. And so it automatically says, okay, these points should probably be laid out on the sky at their positions. But they are hard to see. So once again, so we've assigned this variable layer, which is kind of a reference to this data table as it's rendered in WWT. The rendering engine has this concept of layers, which are different graphical elements that are put on the screen. One of the parameters of this layer is a size scaling parameter, which lets us control how big the points are. And so if I run this command, you should see around now that the points get bigger, and you can actually, hopefully they're more visible now. And so if I scroll around, I can see where the exoplanets in this table are distributed around the sky. I see Peter asks whether this configuration can be, this view setup can be configured for persistence. So the way that it's done right now, it's not very persistent, but actually the new setup plan that I referred to should fix that. So what we have right now is I figured out a way where basically we can add a worldwide telescope as one of these kind of pane buttons that you can just click here and pop one open, and JupyterLab will remember the pane setup that you have, and then your code can connect to that. It's a kind of a single viewer for your entire JupyterLab session, and then that will have that kind of persistence and recovery. And also it's just, you can just click a button and get this viewer instead of having to jump through the hoops I just showed. So that will be a lot nicer, and I think I've got a prototype of that working already. So that should be coming soon, hopefully. Okay, so we have our data table of exoplanets, and this is where they are in the sky. And I said I wasn't going to be adding any code, but actually I just want to check one thing, just see. So this is a data table of just more than 4,000 exoplanets. So the framework that we have here integrates tightly with AstroPi, as you might expect. And so this set of commands here, I'll try and add some new lines just so you can see what's going on. We import some AstroPi coordinate variables, and then there's a function called center on coordinates that will take this view and center it on the coordinates that we give it. And if you are very perspicacious, maybe you can guess what this is going to do. So I'll run this command, and I'll recenter our view. And what you might recognize here is the layout of the Kepler field of view. And what I've done is I've centered our view on the area of the Cygnus region where Kepler was pointing, where there are many, many, many known exoplanets, because that's what Kepler does. And so you can see the footprint of the various Kepler CCDs in the view here. So seeing as our view is fundamentally about visualizing things on the sky or spatially, the RA and DEC parameters of the column are the ones that are kind of the basic things that we use, but we can also use other attributes of the data table in our visualization. And so the way that this all works is it continues setting parameters on this layer variable, and there's a variety of parameters that will affect how the data are rendered. And so the one that we have here, so CMAP at is basically saying what column in the table is used for colorization of these data points. By default, nothing is done, so everything is showing up as white. But this column is an effective temperature column for the host star. And so this is saying, let's colorize the points based on the stellar effective temperature. So if I run that, using the default color map parameters, you should see that everything becomes this kind of purplish. That's sort of just what the default is. We can tweak that. So these next two attributes, vmin and vmax, they set the edges of the scaling used to do that colorization. And so if we clip it to kind of sun-like stars, that's what this will do. So things below 5,000 Kelvin will all show up as the bottom of the color map, and will go up to 8,000. And so that will cause us to have the dynamic range concentrated in where the most interesting stuff is, especially for Kepler, which is mainly targeting sun-like stars. And then the actual color map is the name of a matplotlib color map, and that's a CMAP attribute. And this one in particular is kind of a thermal type color map. So we get things in sort of a red to yellow span that in this particular case is physically relevant. So we can do a similar set of things for also the size of the points. So here we're going to say that the size of each point will map to this column in the data table, which is the planetary mass. And it's in Jupiter masses. We'll set the range from 0 to 30 Jupiter masses. And so if I do that, the view will change a lot, and suddenly we'll have a few that are large and many that are quite small. So this is the kind of thing where, depending on what you're trying to accomplish with your visualization, maybe this is helpful, or maybe this is not what you want to do. I see a question in the chat. Can I change the data points associated with WWT on the fly, or do I have to clear the canvas? So each individual table layer, once you've got a table, that set of data points in that layer is fixed. As we are seeing now, you can sort of change how they're visualized, but you can remove layers and re-add layers, and you can, each layer is independent. So say if I load up 5 tables and I want to get rid of one, I can do that, and I don't have to reset everything. But if I do want to have a data table and then add a bunch of new points, I either have to create a new layer or delete and recreate the existing layer. So you can imagine what's going on here is, in order to create this visualization, the data that we have are in Python land running in some server somewhere. And for this visualization, this is in JavaScript land running on my web browser on my laptop. And so every update of a table, so some things like changing the color map, that message gets sent from Python to JavaScript, and it's just a message about do this for the color map. But if I want to change the actual contents of the table, I have to resend the entire table. And so that's a more expensive operation. So, and so that's reflected where you can't just tweak everything easily on the fly. So this is our 2-dimensional view of the planetary catalog. We also have a 3-dimensional view. And so we'll show that now. And so the next set of attributes about this data layer that we'll set is what's referred to as the altitude parameter. So Worldwide Telescope can also display data anchored on a planet, like you can plot earthquakes and see them below the Earth's crust. And so when you're talking about points in 3-dimensional space, it's spherical coordinates, but so there's a RA-DEC and a sort of distance or radius or altitude parameter, and you can talk about it in different ways. So what we're going to do here is we're going to say that the altitude parameter is the Gaia distance for every point. And so this is saying that when we say this parameter is 10, it will use the unit annotation of AstroPy to say, okay, this is 10 parsecs, and it will translate that into its physical sense. And then saying that this type is distance is saying that it's measuring it as a distance from the 0 center. So when I do this in the 2-dimensional view, I run this code and nothing will actually change. But if I run it, the next command, this will set our view to the 3-dimensional and really 4-dimensional, because it evolves with time, solar system model, as opposed to the 2-dimensional sky exploration view. So this will probably look choppy for you on the screen, but if you run this code yourself, you should see the view transform and center in on what you might be able to see here are orbits of the planets in the solar system. And so this is, we've gone from, there's still a 2-dimensional background, but now we're rendering a three-dimensional view of what is going on in the solar system. And it might be a little bit hard to see here, but if I run the next command, you'll see it change, that my data catalog is still being rendered here. And now it's being rendered in 3D. It's using that altitude parameter to set three-dimensional positions. So if I run this, this is turning off the size scaling because it made some points pretty small. And you'll see this change where things are popping up, which are the plants in my catalog. And so now I've just been panning around here, but I can start zooming out is what makes sense here. So I can do that with my mouse wheel, or you can do it with a two-finger scroll on your mouse pad, or the X key should do it. Now if I scroll out, so solar system will get smaller and smaller. Eventually it will shrink down. Now if I keep on going, eventually we'll see the points in this catalog starting to move. These planets are around, stars that are relatively nearby. And so if I zoom out, now we can start exploring them in three-dimensional space as opposed to just two-dimensional space. And what I've seen here is this is the Kepler cluster of all the planets discovered by Kepler. And you can see it it's still looking two-dimensional, but if I keep on zooming out, I can start seeing how it really forms a cone in the sky, which makes sense because the Kepler stars, they're located on our deck, but they're at all sorts of distances. There's one rendering thing for efficiency, which by default, the engine makes some assumptions about how points are rendered, where it will hide certain points if it thinks they're kind of behind other objects. In this particular case, that's not super helpful. So if I run this particular command, it will set a setting that might cause a few extra points to be rendered. If I keep on zooming out, you might see a sort of faint image here. I actually start getting a model of the Milky Way itself. Peter Tubin says that his laptop is getting hot. Yeah, so again, this is running like a real-time rendering engine. So that is, it will work your CPUs. I personally have gotten comfortable with that over time, but it is different than passively rendering a static image. And the other thing is, as you zoom out to this galaxy view, it will start loading data for actually the Sloan catalog, or DR9, I think, of Sloan galaxies. And so you might get a stutter here where it sort of has to load up this quite large database of galaxy data points. So just give it a try. Yeah, so if I keep on zooming out, you should see something that looks very cosmic webby. And if I start scrolling around, we can actually see that we can start exploring the Sloan catalog in 3 dimensions as well. And so this this 3D model, it's labeled solar system mode, but it's actually a 3D universe mode that goes out to hundreds of parsecs here. And I can zoom all the way in from seeing a bunch of galaxies to seeing the Milky Way. And one thing I want to point out is this Milky Way flat disk image is the only, everything else that you see here is actual scientific data. Obviously, we don't have an image of the Milky Way, so this is an artist conception based on our good understanding of the Milky Way's actual structure. But it's the only artist conception that we have in our core data set. And so I'm zooming in and in and in and in now, and eventually I'll get back to the solar system. And in this particular case, if I keep on zooming in, I'll eventually see just the sun. So I see a question of how do I know what are the WWT set view options? I believe that we've got a, there's a there's an attribute or a method on the WWT object that will list them for you. To be honest, I don't remember what it's called right now. I'll see if I can, oh, available views, that sounds good. And so this will print out the different views that we have. And so the solar system is this 3D mode. The sky is a 2D sky exploration mode. And then most of the other ones are planet views, which map planetary maps to, so you can see right now we've got, we're basically treating the sun as a sphere, and we can map other maps, other textures to that sphere to allow us to, and so this is, for instance, how I can plot earthquake data on the Earth is if I go into this, the Earth mode, I'll be able to sort of say, okay, I can, instead of RA dec being the parameter, it's now Earth latitude and longitude, and I can say it's on the Earth's surface or above it. That's the end of this notebook. So while I'm here, I'll just show that. So I'll do like a set view to Mars. And this will start being zoomed in. And so if I do that, we have our nice 3D Mars planetary view, which is just kind of fun because a lot of what Worldwide Telescope does is it has the textures of the planets, and they're ultra high resolution, but it streams them in progressively as you zoom in, kind of like Google Maps. And so I can go from being way out in Mars to zooming in, and it will tile in higher and higher resolution data. And so, if you're doing stuff with like planetary mapping or things like that, I'm really not aware of any software that will let you explore the data in a comparable way. I see Peter Tubin asking one, sit at the galactic center. No, we don't have that as a built-in kind of option here. Although, if you zoom out, I mean, you could certainly, I think right now you would have to, like, if you wanted to display data that were based in galactic coordinates, I think you'd sort of have to do the transformations yourself. But it's a generic, the 3D engine has this kind of scene graph structure where you have reference frames that then, there are sub-reference frames that move with them. And so it's able to deal with stuff like changing reference points quite effectively. I also see a question, is the image of the sun based on actual quasi-real-time data? Unfortunately not. One thing that's a little bit annoying is, if we've got the full sphere of Mars here, say, and that's how we want to render things, we can't do that with the sun in real time because we can only see half of it once, modulo the stereo satellites and a few things like that. So you could certainly, in principle, you could stream those data on and map them to, we have a lot of framework to, you can certainly ingest new data, new sphere maps into the system. So you can stream that data in, but it would certainly be a little bit awkward to have one hemisphere that's really well populated, and then the other hemisphere you'd have to in paint the way that people do with the CMB or something like that. So let me just go back to my slides. I don't think I actually had anything particularly more to say about that. Yeah, so we've seen how to display an AstroPi table in the sky and control things like colors and sizes, plot in 3D as well as 2D. Yes, and plot as a function of time. So that's another notebook. So if I switch back, so here I'm going to have to close this output view and close this exoplanet notebook. And if I go back to the start here notebook, I see Peter asks, when displaying the BMassJ view, I get a huge bright circle covering most of the image. Is the effect of using Firefox? I do most of my work in Firefox, and that doesn't happen for me, so I don't think it's that, but that sounds like you've run into some kind of bug. If you wouldn't mind reporting it on our GitHub, where I'll type in a GitHub URL for you. then we can look in that. But because, yeah, that sounds like some kind of WebGL bug. That's the, I'm not sure where that answer went, but that's a GitHub repository where you can file an issue for that. So getting to the time axis, the next notebook that I'll open is called the time axis, gamma ray bursts. So if I'll click on that, this will open another notebook, and it will have a similar sort of opening stanza. And again, the way that things work right now, for each notebook that I open, I have to open a new widget. But again, I think we've got a concept for how to avoid that overhead, which I think will be pretty cool once we get it deployed. But I have to port a lot of our raw JavaScript to TypeScript, which will be a good thing, but will take a little while. So once again, I've run these commands to import our PyWWT module. This will be a little helper function for opening data, create the widget. And so once again, I'll go through the dance of find this blue bar, right click, create new view, close old view, drag tab over here, wiggle around till Jupyter figures out what I want to do, let go, and then resize. And so we're back at this initial view. Set up again for this new notebook. And so now I'll work on a data table and show some support that Worldwide Telescope has for a time axis in a data table. And so this is going to be a data table of GRBs running through 2016 or so. So I'll run some code that will import a bunch of AstroPy stuff, and then we'll read this GRB table and again print out the first few columns, and so, or the first few rows. And this is a very simple data table of just RA, DEC, and GRB time in a Julian date. So for what we want to do, as far as Worldwide Telescope is concerned, these are just numbers. And so we need to convert these Julian dates to AstroPy time objects. And this is the bit of code that will do that. And so, you know, it shows up as a string here, but you can, so what we do is we format it as an ISO time string, which is what Worldwide Telescope keys in on. And so you can see that these GRBs are starting in 2008. And I think they go up to, oh, down here it says they go up to 2014. So once again, we'll take this AstroPy table, which is a variable called bursts, and we'll add it to our layers. So this is a new view, so we don't have the planets anymore. And here we'll be a little bit more explicit about setting up some of these parameters. And you can, what we're showing here is some of the things that I set after the fact in the previous notebook, we can set in this function call as keyword attributes, and it will do the sensible thing. So if I run this, we'll see a bunch of points. So right now, WWT isn't paying attention to any time axis, but what I'll do in this next couple of lines is we'll say, okay, this dates ISOT column is a time column, and we'll say, pay attention to it. So what will happen when I run this is everything will disappear, because Worldwide Telescope has an internal clock, and by default, it matches your system clock. So if I run this get current time, this should pop out. It's running 2020, November 8th. And our data table only goes up to 2014. And the way that the time support works is points in your table, if they have an associated time, they'll appear at that time, but then fade away over some time scale. And so with the default parameters in how this is set up, everything is faded away because all these GRBs are very old. So as a little demonstration, what this next chunk of code will do is we'll find the first GRB in the table, we'll navigate the view to where it will appear on the sky, and we'll set the WWT clock to 5 seconds before the time that this GRB goes off. And so we'll center the view and we'll set the WWT internal clock, but it will keep on running. And so after I run this, 5 seconds later, we should see a little dot appear, which is that GRB going off as far as WWT is concerned. So if I run all this, my view will warp somewhere, and the timing might be a little bit funky, but for me, it just appeared as hoped. We got this little dot. Once again, I mentioned that the way that the time axis is handled, these things will appear and then they'll fade over time. The default fade time is 16 days. It's just kind of an arbitrary, there's no good sensible thing for that. We'll set that to be larger. So here we'll set the decay time to be a year of WWT clock time. And now what I'll do is this function will set how fast the WWT clock runs. So what I'll do is I'll set it to run at 3 million times faster than real time. And so what this will start happening is I'll start seeing GRBs popping off all over the sky because, now 1 second of my time corresponds to, you might be able to see here the planets moving around because in this 2D sky view, Saturn just went into retrograde. In this 2D sky view, planet iconography is overlaid. And so if you can find the ecliptic when you're doing this and seeing the planets wiggling around, it's pretty fun. This command will set the clock to go back to running at real time, or at least real time according to my computer. And if I get the current time and look at the difference, I can see that approximately 1,209 days passed while I was letting everything pop off. And in the view that we have here, you'll see that some points are brighter and some points are fainter because these GRBs have been disappearing over time with this sort of fade parameter that I set. So in this particular case, because GRBs, as far as we're concerned, are infinitely far away, if you had distance information for them, you could actually add that and zoom way, way out to the Sloan Galaxy view and maybe explore them in 3D. But we don't have that information in the data table, so we're just going to stick with a 3D view where one of the dimensions is time rather than distance from the sun. I see a question. Is there an easy way to turn off the planet iconography from the view to conserve resources, or is it negligible in terms of overhead? It's negligible in terms of overhead. So the view that we have here is based on WebGL. And so, we have WebGL shaders that are rendering these data tables, and the planets are just like little graphics that are overlaid. And so it's a WebGL, again, it's like a game engine where it's rendering this scene continuously. And so adding a few extra textures is no effect at all. So that was a brief demonstration in this notebook of that. Jessica asks, can you display the time on the image? Not in the view that we've got right here. The way that you get it is this WWT get current time function will get that information for you. In web apps built on the WWT rendering engine, you can certainly extract that. And this is an HTML canvas with some code that's running WebGL, and you can overlay all sorts of stuff. So you can have that sort of thing, and that's actually one of the things we're thinking about. What we want to add for that is you could add readouts to this kind of thing. And Malcolm asks, how do you know where the view is located? And similar to the get current time, there's a wwt.get. Forget exactly what it's called, and so I'm trying to tab complete. There we go. Get center. which will pull out the center of the current view as a AstroPy sky chord object. Does it show? There's a way to turn on crosshairs, so that coordinate corresponds to the center of the view. Rosa says, I cannot zoom out beyond a point. Is this rendering limited to a certain size? Yeah, there is an ultimate limit to the zoom out, although in the default, so in the two-dimensional mode, the limit of how far you can zoom out is so that the height of your viewport is 60 degrees. In the 3D mode, you can zoom out, and it's it's more of a physical scale in the 3D mode, and that's like something that's the scale of many, probably gigaparsecs. In the Windows app, eventually when you zoom out, it shows you the CMB as a sphere. In this version, with the web version, that particular little feature hasn't been ported over, so it doesn't do that. You can change that limit in the 2D sky mode. That's one of the parameters in the engine of what that maximum zoom out is. But once you hit 60 degrees, like if you start scrolling around, it's a tangential projection, and you start seeing some weird distortions that become a little distracting for most cases. All right, so that's all that we had for this particular notebook. So I'll close this view again and close this notebook, and maybe shut down that kernel while I'm here. So if I go back to my slides, so plot as a function of time, if you want to play around with this stuff, I'll transition to talking about imagery a little bit, which hopefully I won't just be talking for too long. But again, one of the beauties of these cloud-based notebooks is you can just sort of fool around whenever you want. So if you want to experiment and load your own data tables and see if you can get them going, now could be a good time to do so. And I should also say that in the Discord, as you might guess, the documentation for PyWWT is at pywwt.readthedocs.io. To be honest, like the documentation isn't like incredibly thorough and polished. We could do a lot more cool stuff with it, but it should at least kind of give you the API surface and a sense of the different knobs that are available for that. And if you have any, if you look at the documentation, there's any questions that are missing, or things that you figure out that you think we should add, please let us know. We'd love to improve that stuff, especially again, because what we're doing is fundamentally rendering stuff in the web browser. We can we don't have it set up right now, but we can include interactive worldwide telescope views inside the documentation, which hopefully should be pretty cool. And so I feel like the questions have been coming in at a nice pace so far, and hopefully I've been answering them. So if you have any additional questions or comments, please keep them coming. But I don't think I'll pause for too long for this right now. So the next section, we'll be looking at loading image data. So just to orient a little bit, in the same way that we have these layers for tabular data, which inside WWT, they're called spreadsheet layers is the terminology. There's also image layers. And the Python interface for working with those is quite similar to what I've shown before, where you add a layer and you get a variable that then lets you tweak how that layer is presented. So I'll show some operations with FITS files here. Most of what WWT can do is, or it's got more functionality when it comes to so RGB images like JPEGs or PNG files, or in particular, WWT has functionality where I can take a very large image say the fat mosaic of the Andromeda Galaxy, which is, I think, 3-point-something billion pixels. And it can use its progressive multi-resolution capabilities to let you view that image and zoom way in and explore it on the fly and stream it all, yada, yada, yada. Right now, that only works with images that have been converted to, RGB mode of like a JPEG or whatever. We have an NSF grant to extend that functionality to also include FITS data, or essentially floating point data, as opposed to 24-bit color data. And so what you need to do there is you need to downsample the image and break it into individual chunks, tiles, because the whole issue is we can't download the multi-gigabyte file into your browser all at once. So you need to do a data transform to make that possible. So we've got the support to do that, but just right now, the existing infrastructure only renders RGB type images, but we're gonna take the FITS functionality that we have and this progressive multi-resolution functionality that we have and mash them up. And so that will mean that you'll be able to say, take an entire LSST tract and explore it as you would in DS9 or any other kind of scientific image analysis program. We're still building out the functionality for image processing, so I think we've got the core stuff that's pretty useful. But there are a bunch of features that we don't have, and we're certainly happy to add whatever would help people do their work. So I'll switch back to my notebooks here, and the next one that'll open up is the one that's called Visualizing Imagery. So if I click on that, we'll open up a new notebook, and once again, I'll go through the dance of importing our PyWT names, create this little helper function that will help me load my data files, create that widget, find a sidebar, create a new view, close up the old view, grab the tab, drag it over, wiggle around until Jupyter knows what I want to do, create it, even things up, and we're good to go. So yeah, once you get used to this dance, it's not too hard, but I think it will be nice once we get our new framework in there and we can streamline a lot of that process. So to add an image, there's a function called add image layer on this layers interface object. And if you give it the path to a FITS file, it will basically do the sensible thing and load up the file and add it on as one of these image layers. So what I want to point out here is that this, if you're using these notebooks in the cloud, there's essentially a Docker container that's powering this Jupyter interface, and we have this FITS file preloaded into that Docker container. If you didn't have that, if I click on the icon here to open up this file explorer view, there's an icon here where I can upload files, and this will open up, maybe you'll see this. It'll open up a file browser, and so I can upload data to this Jupyter instance, and then you can add an image layer using the same sort of, just a file path. If you give it a file path on your local machine, it won't know what to do because this Python code is running in the cloud on the server, not on your local machine. But if you have your own image and it's not too large to upload, you should be able to upload it and see if you can play with it yourself. So if I actually run this line, it will take a minute because it does have to get the image data and transfer them to the JavaScript layer. And by default, it will steer the WWT view over to where this image lives on the sky. And this is W5, which I think is a star forming region. I don't actually know. And so that might have been jerky in what you saw here, but it's a very nice kind of smooth steering effect if things are operating properly. So now I have this variable layer, which lets me have controls over this image. And one thing that we've done here is you can control how the image is rendered using Python properties, as I've demonstrated before. We also have a special variable called controls, where if I run the cell containing it, it will pop open a few widgets that let me set how the image is visualized. So I'll try and see if I can resize this a little bit. So it's still a little bit wide for the view that I've got here. But this gives me a UI a little bit easier way to control how this image is rendered. So for instance, our default color map is the Viridis one. I can change it to different options. Try Inferno because that sounds cool. I can change the stretch. So we have some of the usual sort of options here. So I can add a log stretch. And then the opacity slider is one that's particularly cool because that's the kind of thing that WWT can do, which isn't always convenient. And I think a lot of the power of this particular rendering engine is being able to take a data set and compare it to other data sets and view it in context. And so if I can control the opacity of my image and fade it out a lot and crossfade interactively, I can see, okay, where are their sources in this image and what other images I've got pulled up or whatever background I've got pulled up, or in a moment I'll show how you can compare different things there. And so again, this is the thing which in the way that Zoom streams things might not look very nice, but you can fade the image in and out interactively quite nicely. So there's also min-max controls to adjust how the fits data are color mapped. And so the way that this interface works is there are coarse and fine settings. And this fine setting, there's sliders that you can drag around interactively. And then these coarse boxes set basically the edges of this slider control. And so the values are filled in from some defaults taken from looking at image percentiles. But for instance, what I could do here is right now I don't have a lot of dynamic range in these fine controls, but say I can change this minimum, keep it about the same, and then this maximum is clearly a lot bigger than as is commonly the case with pixel value distributions. There's a few very bright pixels that are driving this coarse one up a lot. So if I set this to more like 1000, that means now if I drag the sliders around, this value is 420 and this value is 1000, and I can drag it around interactively and set the cutoff point a little bit, set it interactively and not have to just be typing in numbers. See a question from Bruno about, is it okay to share these notebooks? Definitely. These are all public, and there's nothing ADAS specific in what we've got right here. Yeah, so that bit.ly PyWWT notebooks link, that's the permanent link. It should always be available. And again, this is part of it is this is running on my binder, so we don't have to pay the server costs to serve up these notebooks on the cloud. It's a very fine service, so thank you, Google, and everyone else who helped support that. And so I can also, one also neat thing is if I move the minimum up, the default behavior is that things below the minimum turn transparent. So I can get this effect where I can, see through the source image to the underlying background imagery, but I won't do that right now. So once again, these controls can also be accessed through Python variables. And we're using the IPyWidgets framework here, where it's got a nice setup where these widgets and these values and this view are all linked. So if I run this code, it will set a bunch of values. And you'll also see that up here, the widgets will update to match them appropriately. And one thing I haven't shown before is there's this reset function, which will throw away all the layers and reset the view to default values. So that's sort of basic image loading. So as I showed before, that was with loading a FITS file that is baked into this server. And so you can imagine if you're running Jupyter Lab on a science platform, you might be able to access FITS files directly because the kernel will be running on a file system that has access to it. But one thing I think is neat is kind of showing how in this web paradigm, you can really start stitching together different things. So next we'll use the AstroQuery module to pull down some images on the fly. So what we'll do here is Skyview is a service from Space Telescope, I believe, that will let you pull down FITS files. So you may see up until recently, this part of the demo used 2MASS infrared data. But I recently discovered that that seems to be broken in Skyview right now, so I've changed it to use, nope, sorry, Skyview is HESARC. Apologies. So 2MASS has problems right now, so I've changed it to use SDSS. So the variables will be called 2MASS, but the data are actually going to be U-band Sloan. So that's just a workaround where I didn't rename everything. So what we'll do here is we'll do a query for the position of supernova 2011 FE. We'll set the image size, and this should pull down. The variable that we'll get here will be an AstroPy FITS object, so not a path to a FITS file, but it'll be downloaded and loaded into memory here. And this one will take a minute to run because it's actually going to the Skyview service and downloading this data on the fly. And so we print out the FITS info, and so, okay, we've got a FITS file. So once again, this is like a FITS HDU list, and I can just pass it to the add image layer function, and it will do the sensible thing. So we've pulled up this image and zoomed in on it. And one thing I'll show here is what I alluded to before is the default background that we've got is scans of digitized sky survey plates and do an RGB composite with enhanced extended features like cool galaxies and planetary nebulae and things. So it's a good all sky reference map. But obviously you might want to compare against different kinds of maps. I should say the DSS has this unfortunate problem where there's kind of an arc-second scale astrometric offset. Some of the other maps that we have don't have that, but if you are doing things at that level, you want to make sure that you're comparing against a different data set. So I can set this background to a different one. So in this particular case, I'll pull up 2MASS. And you'll see, so this is tiled in and it's lower resolution, which is one of the trade-offs for the 2MASS data set. But I can compare this image to this background. As with the image controls, we have a special variable called layer controls, where that lets you set the parameters of the background imagery. And what you can actually do is, that's a shame. So if I squeeze this over, hopefully you can see, you can load up two background data sets and blend between them. So right now I've got 2MASS loaded up, and I've got this DSS data set loaded up, and I've got the blender all the way to 2MASS. If I drag this over, I'll go back to DSS, or I can have a combination of the two. And if I click on this drop down, you can see the big list of options that we've got, which is pretty extensive. So, I can compare against a whole bunch of these. I can pull up my low frequency, or sorry, This is actually NVSS. Can pull up my radio data, and just for fun, if I'll zoom way out, you can see, you know, sort of the radio deconvolution artifacts of the that I get from NVSS and pull back in. And once again, these controls are wired up to Python properties that I can affect. Mateo asks, is there a way to invert the color map? Yeah, there is. So I can show that in a second. So if I run these, this Python cell can set the default back here, and I'll make this view a little bit less wide. If you're running it in a standard environment, I've got my screen set to pretty low resolution here so that everything will be legible. On a bigger monitor, there shouldn't be any issues with kind of having things in a side-by-side format. So now what we'll do is we'll add another image layer. This is using another FITS file that's stored right in the repository, so I don't need to download it in advance. And so this will overlay this Swift imagery of around the location of the supernova. And I can pop open control widgets. And so I've got these two different image layer things where I've got these graphical controls, but they apply to the different images. And so I can crossfade and, you know, blend in Swift a little bit, and then, you know, say make, again, it's called 2Mass, and it's actually Sloan right now. Blend that back in. And so some of these color maps, you know, we've got like black to white and white to black, so that's inverted. We might have a better approach. I forget whether we have a, we might have a knob that lets you sort of invert things manually. So if I tab complete on our CMap options here, I feel like it takes the tab complete a while to pop things up, or am I just not? Yeah, so one thing you could do is the CMap parameter will take any matplotlib color map name. I believe that matplotlib has inverted color maps for everything. I don't know exactly how you refer to them, because I just like matplotlib so much that I've written my own plotting package instead. All right, Viridis R, cool. So I guess we can give that a try. Oops. Okay. Oh, that's right. Yeah. So we have to use only a certain subset of the available color maps. So I guess the reversed version doesn't work. I see a question from Mateus. Is there a way to enable coordinate lines RADEC as L? Yes. So this is another one where I don't use it personally, but okay, yeah, so like ecliptic grid, if I turn that on, that should eventually show, yeah, ecliptic grid lines, and there's other settings for equatorial and et cetera. So if I scroll back before my embarrassing exceptions, so we've got interactive controls that let us do a lot here of comparing multiple images. And so you can play around with whatever kind of visualization. So here I've switched it all over to, this is saying Fermi. And one thing that I've found that WWT is very good at is giving you a sense of the resolution differences between different all sky surveys, and you know what is generally achievable in different bands. And so you know, at the level at which we've got these optical or IR data, you know, the gamma ray data are just incredibly low resolution in comparison in this particular case. And so I feel like being able to overlay images like this really helps you get a sense for the challenges of multi-wavelength astronomy. So that was all that I wanted to show for this notebook. So we've shown a couple different ways to pull up images and to control how they're displayed. And again, I think you can imagine a lot of ways to kind of make this more effective and easier to interact with, depending on what your goals are. So I think, what we really focus on is, some things that you might do with DS9 of like pixel level statistics, and overlaying regions and kind of the really fine scale stuff like that is probably not as good a match to what WWT does well. What we really do well is this overlaying data sets and comparing them and understanding your data in context and doing things like being able to fade in and out and look at what sources are visible in what bands, and being able to zoom out. And if you do something with extended structure and seeing, okay, does this structure line up with something that I see in the SFD dust map or whatever else, that's where this kind of view I think has its greatest strengths. So I'll close out this notebook and flip back to my slides briefly. So we looked at displaying FITS images, and I would certainly encourage you, if you've got a FITS file on your machine, again, it can't be too big, but you can upload it to this JupyterLab instance and try and get it into WWT. And internally, we use, again, AstroPi's FITS support and the reproject module to transform things to what WWT uses as a tangential projection. So if you've got stuff in other projections, we're using kind of the Python WCS stack to work with things. So it should be able to handle pretty much anything that you throw at it. That's, we're plugging into the standard architecture. It's pretty well built out at this point. I see a question from Laurent. Can I get a human readable description of my view? Not beyond the things that I had with the way that those widgets will display. We've got Sloan and Fermi, and we're blending between them. There are ways to export those views, which I think is the next thing on the agenda. Yeah, so if there's any additional comments, feel free to type them in and I'll try and answer them. I think if I'm paying attention to the clock correctly, I think sort of moving at about the pace that I was hoping for. So move on to the next section. And I want to get a little bit more into this idea of, the way that having things be on the web and be browser-based allows us to stitch together software in a way that, astronomy has been pretty good with things like SAMP for having different applications talking to each other even for a long time. But a nice thing about the way that I think of it is that the web is really the universal platform for applications and user interfaces going forward. I think if you look at both the directions within astronomy and within computing in general, the web is where everything is happening in terms of user interfaces, and because of that, we have things like WebSockets and XML HTTP requests and all these things that let web applications talk to each other, and that's sort of how we are stitching together applications in the 21st century. And so that opens up a lot of exciting possibilities for, sort of this decentralized software paradigm that I think a lot of us have, found very exciting for a very long time. So this is some words along these lines. So once again, I think in particular, AstroQuery is a really cool resource to have out there, because it bundles a lot of these, web API queries and provides the data in a standardized way, which, not coincidentally, we mesh as well with things like PyWWT. So one thing I do want to emphasize is that, the core of what WWT does well is this rendering engine that can render images and data tables and has a big data library using WebGL. And all that stuff is JavaScript code, not Python code. You know, PyWT is actually a fairly thin layer that basically gets data from Python and allows you to get it into this JavaScript rendering library. And it deals with the bridging of the way that Jupyter works, where you've got a browser front end with JavaScript and a Python backend, and those might be running on different machines. And PyWT deals with all that bridging that has to happen in that particular user interface paradigm. But all the heavy lifting is in that front end that knows all the coordinate transformations and knows where the data are and can stream them and has all that infrastructure. A nice thing is once you've got data into that rendering engine, again, it's web-based, so you can run it anywhere that a web browser runs, which is everywhere. And I haven't updated this slide as much, but one thing I want to point out is that the code, you know, it's a JavaScript library at its core, but we are adding more and more TypeScript interfaces to that you can use. And so if you're not an expert in this stuff, TypeScript is kind of a superset of JavaScript that has a compiler. So there's things, you know, if you reference a variable that you make a typo in a variable name, you'll actually get a compiler error instead of having your code crash on you. It compiles down to JavaScript. And so, you know, the library that we have, you can always use it from JavaScript, but if you use it in TypeScript, the interfaces are better defined and there's nice tools for generating documentation. And so in particular, we now have a layer that lets you integrate this rendering engine with the Vue and Vuex UI libraries that are quite popular. So there's a nice platform for building web apps, which is a lot more sophisticated than what you can do with just JavaScript. I see a question from Durant. Is there a resolution limit for displaying and manipulating an image? So essentially, no. I've gotten the EHT black hole image ingested, and if you zoom in close enough, there you start running into floating point precision issues because this is WebGL stuff. It's half precision floats mostly, or single precision. So once you get down to micro arc second level, you run into issues. And as I said before, it is true that where WWT excels is in sort of this comparing images against context. And so if you've got something, if you've got stuff that's, you know, if you have a single image that's very high resolution, our contextual imagery might not help so much. Then you know, maybe another tool will be more appropriate. But in terms of the technical limitations, we start running into floating point precision issues sort of at the micro arc second level, but beyond that, it should work well. Peter is commenting that, yes, the flip side of everything being web-based is that you do need good internet. And especially, you know, we are streaming a lot of imagery. And so it is a fairly bandwidth intensive application. Yeah, you know, that's definitely a genuine issue. You know, the way that I think of it is, you know, there's part of my job working at AAS is being involved in the publishing section with the journals. And, you know, there, when it comes to this kind of stuff, we worry a lot about reproducibility and longevity. You know, will this app work 100 years in the future? And, you know, as things get more complicated, you can create more cool effects, and you can, especially when things spider out, you know, you can do lots of really neat stuff, but there's that trade-off of durability and robustness. For instance, that issue that I discovered where the notebook that we had originally, you know, had stopped working because Skyview's link up to the 2MAS data is not working right now for some reason. And, you know, this is, I think, just as things get more complicated, there's going to be more points of failure. And as they get more networks, there's going to be more points of failure. And but at the same time, that complexity and that interlinking is providing a lot of genuine value. So I think there's ways that you can use cleverer or less clever engineering to if you can avoid dependencies on services that aren't necessary, then that's probably a good thing. But there's a fundamental issue of some of the things that we want to do are fundamentally involve networking things together, and that fundamentally makes things more fragile. So yeah, this is a genuine issue, and I don't think there's sometimes when there's just design choices that can help, and there's some things which are just inherent. Jose asks, can these notebooks be converted to static HTML files and have the PyWT layer still working? Partially, so that's what I'll try and be showing. But yeah, so fundamentally, what we show, the interactive thing is an iframe that's running code. And so if you get the right HTML, you'll get that interaction in a flat HTML file, which is what I'll try and show here. So getting back to the slides, this is the same sort of thing that I've just been saying. And I do want to emphasize that one of the reasons that AAS is supporting Worldwide Telescope is we're very interested in interactive figures and journal articles because, I think genuinely they do offer a view that lets you interact with, say, an image or a time series, whatever it might be, really does convey information and insight in a way that static images don't. And so we're interested in building up the infrastructure to allow people to actually be able to create those images and publish them and access them. Genuinely opens up new possibilities for communication that have not been possible, literally since the invention of the printing press. So show a little bit more about that and also show this HTML export. So for this, I want to open up the creating interactive figures. I worry that this might mean that my Binder Hub instance, I'm going to guess that Binder Hub has shut down my server because it's been running for a while. So yeah, so fortunately, because we're running in the cloud, I'll just start it up again and I'll get a new one. And this hopefully won't take too long to get running here. Yeah, that's nice. So where were we? So I'm going to be opening up this creating interactive figures notebook. So the instructions here are slightly different, but actually they're outdated, where we had some technical limitations that were causing issues with how we, with this particular workflow, but those should be fixed now. So I'll once again do the setup and create my widget. And create a new view, hide this old one. Generally, I find that the limiting factor in this these days for me is Jupyter Labs tab manipulation can get a little wonky. So we're going to repeat what I showed recently with importing some images. So I'll use this existing file. And again, it will take a little while to fetch the imagery and then load them into the JavaScript layer. We'll pan over and show that. And can pop open some controls that, again, if I want to, I can play around with how things are rendered. Maybe we'll try Plasma. So in terms of this HTML export, so you can save a notebook, a Jupyter notebook as HTML. And if I've popped out this widget, then the HTML for this viewer won't be included in sort of the notebook export. But what we do have is, so there's a special function that we've added called save as HTML bundle. And that will basically serialize the current state of this widget into a zip file containing, sort of the Java, an HTML wrapper, setting up, loading the necessary JavaScript libraries and things, but also serializing the underlying data and the state of the viewer. And so if I run this, you won't see much happen. But if I pop open the File Explorer here, in a moment, what I should see is that this figure.zip file will appear in the file system running in this cloud thing. And what's nice is that I can click on it and right-click and download it and save it to my machine. So at this point, I'll show a little bit about what's going on in this bundle. This is stuff that won't be happening in the Jupyter Notebook, and so it would be trickier to follow along. But just in case you're curious, I think that might be a nice thing to see. So hopefully if I pull this up, you should be able to see a terminal window. Oh, it should be. Okay, this will be a test file that I created yesterday, but I didn't do a whole lot to customize anything. So won't have any important differences. So if I look at this zip file, there's an index.html, which again is sort of an HTML wrapper that loads up the WWT engine. There's some metadata in a JSON file, and then it's cut off right here. But we're also including the fits file in this zip bundle. So that's why it's a big file. This is about 4 megabytes of fits. And so, if I use this as an interactive figure in a paper, one of the side effects of that is that my figure has the fits file attached, which, if you've ever seen an image that was scientifically relevant to you and you wanted to, explore it yourself, and you had to email the authors of the paper, then, just having the fits file attached, I think could be a really game changer. Peter Tubin comments that you can less a zip file. I can, because I have a special, you can add wrappers to less that add filters to things that let you define special actions for certain file types. So I've got my less set up where, like, if I look at a tar file, I can see the listing. If I look at a zip file, I can see the listing. It's very handy. It's on my, okay, Peter says it works in vanilla Ubuntu too. So what I'll do here is I'll unpack this zip file. And so now we've got these files here. And I'll just start up a little one-line local file HTTP server. There's many different ways to do that. The one that, oops, that's not gonna work. The one that I prefer is this npx HTTP-server version. Get some things right with content types that some of the Python version doesn't. So now if I open up, so I just have like a little local HTTP server which is serving up these files, and there's an index.html. So if I go to this address, oops, I don't know what that just did for you, but it probably pulled us to the wrong place. So if I go to my web browser and navigate to that address, we see, basically a reproduction of the image that I had here, except, right, we have a bug where the color map doesn't propagate. The choice of color map doesn't propagate. But, unlike a static export, I can zoom in and check out the underlying data, or zoom out and see where this image lands in galactic context. So yeah, we do have that one bug here, and There's certainly more that we could add. So in this kind of standalone view without any associated Python, having a coordinate readout or a time readout or some widgets to control the view would certainly be helpful. That doesn't happen right now. But this is this file. So if you submit an article to the AAS journals, AppJ or whatever, you can use their interactive figure support and just send the zip file, and you can get this in your published article. To go into a little bit more detail there, it's not really worth showing, but there's some most recent versions of the AAS Tech LaTeX package. There's some special commands that you can use to point out that you want to include an interactive figure. And so, if you're compiling your tech document to a PDF cannot include an HTML iframe as far as I know. So you won't have it there, but it will have a placeholder. And in fact, one of the rules of interactive figures is for every interactive figure, there has to be kind of a static version. Again, for kind of long-term durability, interactive figures are adding value, but we do recognize that they are kind of fragile in a sense. And so the static version, we actually require that to be provided to have something that is, doesn't provide the extra interaction, but is going to be more durable. Question, are these interactive figures allowed in the research notes? Yes, they are. I'll pop this over. So just to continue talking about this, so this HTML iframe fragment, again, it's pretty much a self-contained web page, and so you can use it in anywhere else that you might use HTML. And so, for instance, the line wrapping here is a little unfortunate, but if you unpack these files, you can just, if you have some kind of web publishing platform where, which allows you to get an HTML iframe in there, then you can include this interactive figure in, your data portal or whatever it might be. I think this is something that we're building out some infrastructure for, which I think is getting pretty cool. Yeah, so this example is the text here. If you want to revisit it later, shows how you can do what I just did to pop open the figure in a personal browser. So I'll pull up here. So if I go to docs.worldwidetelescope.org, this is our documentation hub. And I'll just paste that link into the Discord. If I scroll down, so the WebGL engine is what we refer to this TypeScript library as. And so as a little reference here, this is our more sophisticated embedding app, where this is one of these planet sphere views with Mars, where you can zoom in and navigate interactively. And we've got a few interactive controls, including setting the view full screen, which I think is pretty fun for a display like this. And so this is using something that we call the WWT Embedder app, which has some functionality that adds on a few more of these little UI elements that make it the standalone HTML nicer to view. So if I go, say, to our WWT forum, but this should be nice. So here's our embedder being used in the forum, where this is a recent image from Noir Lab with a nice DECAM mosaic of the Milky Way bulge. And so I've got a UI widget here where I can pop open a control and open a crossfader, and I can do this kind of interactive fading without needing to do it all through Python. So this is what we're going to be working on, is sort of beefing up the connection between the Python controls for this and the standalone HTML controls, because this is just something where we've got wired up to our discourse instance where you can include these things and embed data. And so this, let's see. So this is 50,000 by 25,000 pixels. So if I zoom way in, I can see every individual little star here. And if I crossfade out to our arcsecond DSS image, you can see the improvement, although you can also see the unfortunate astrometric offset in the DSS image there.
Peter, there was one question here, is about the exported HTML that you showed.
Mm-hmm.
Do you still need an internet connection to actually, look at it? Meaning, does it, have to fetch something from WWT at all, or not?
Yeah. So, so if you think about the zip file structure that I showed, so that underlying FITS file in that case is bundled into that zip file. So the FITS file is right there and not relying on any services. But the background imagery is streaming things from the Worldwide Telescope data APIs. And so you can imagine doing a sort of preload concept where maybe you open up the initial view and maybe we bundle in the imagery that shows up right here, so that to make it more self-contained. But then if you want to navigate over to this part of the sky, then maybe it starts pulling down fresh data. The backing data sets for all the contextual imagery at all the resolutions add up to tens of terabytes of data. So we can't include full flexibility for that, but certainly when it comes to this idea of limiting bandwidth usage and making things kind of more robust and long-term stable, yeah, we have some thoughts about there's things that you could do to make it a little bit more self-contained. Yeah, and so I also wanted to show here, another one of the controls that we have is this version has slightly more limited controls, but you can say, pull up the SFD dust map and see how this image compares to that. And that's heading my viewers here. And so once again, I think this is, I'll put this back to the main optical map and maybe full screen it. And yeah, so this is, a 100 million pixel image that we're able to view from all the way out to zoom way in and see individual stars once they stream in. And so I think this is just like a really cool capability for exploring large images, which of course are becoming quite relevant and more relevant with the way that astronomical data are going. And because it's all on the web, it's going to work in Jupyter. It can work for these kind of standalone applications. I do my slides in HTML, so it works in my presentations. Not everyone is going to do that. It turns out to be a bit of a pain in the butt, but it does let you, I can give a talk where I can include an image and explore it interactively and change the, change the stretch depending on the lighting conditions of the room. Haven't done that in a while, but once we start giving in-person talks again, that should at least be a useful thing to do. So that was just an example of a few examples of what you can do, all building on the fact that fundamentally what we're doing here is we're using HTML and JavaScript. And the web industry has poured tens, hundreds of billions of dollars into building efficient remote data visualization toolkits, those toolkits being the web browser platform. And so building on them, I think, is the future of this kind of interactive data analysis. And that was all I had for prepared material. I think we've got about just a little bit more than 10 minutes left on the clock. So I'm happy to answer any additional questions and show anything if there's any other ideas that people have. If you want to play around with the notebooks yourself, now is the time to do that. And again, if you have any data on your computer, I recommend uploading them to this binder instance and seeing what you can do. So Rosa says, I tried opening the index in my browser. It doesn't show the image. It's just black. My guess would be, so one thing that is important is if you open up the index with file open or go to a file URL, the interactive stuff won't work. So there's actually limitations in what web browsers can do with local file URLs that break some of the stuff that we do. It's actually more restrictive in a certain sense. So my guess would be if you did that, as opposed to starting up a local HTTP server, that might explain why it's not working. It's a little bit annoying, but yeah, that's just how it is. And so for more and more, like if you have things that will compile Markdown, they'll serve them where you go to a local host URL, opening it just through the web browser as a file turns out not to work. Peter, yes, he mentioned 3D cubes earlier. Asked if that code is still working in WWT. I don't think it's wired up in the web version of WWT. I think that was only in the Windows version. And so what we've got is the code that powers the web version is derived from the Windows application, which is written in C#. And so our build process has this thing where the C# code is translated to JavaScript, and then we wrap it in TypeScript to make things a little bit more polished. Unfortunately, it's a fork of the Windows app, and so there's some features in the Windows app that haven't made it into the web version. But I will mention, right this very moment, last year, the group at China VO developed support for the HIPS format for all Sky data sets in their version of the Windows app, and we've ported that to the AAS version of the Windows app, and we're now porting that to the web client. And so our all Sky data are in a format called Toast, which has some very nice technical characteristics, but it's not as widely adopted as HIPS. But we've got our first HIPS data rendering inside the Worldwide Telescope web engine, and possibly within months, we should hopefully have that HIPS data rendering ready to go in the web version. So that will allow us to add a lot more recent all Sky data sets for contextual imagery, which should be really great for research stuff. Bruno asked a question about, I've showed these things running locally with Node.js, and wonders if it's possible to wrap the app up in something like electron.js to write a custom desktop to display local data. I haven't tried it, but it should work. I mean, this is the beauty of building things on the web platform, you can take advantage of all this kind of work. And so I have to imagine that Electron works with WebGL. That I think would be the main thing to wonder about. And it seems like the kind of thing that I bet people have spent time making sure that works. So I haven't tried it, but I would strongly suspect that, yeah, you could bundle this into an Electron app and make it something that works locally. All right, I see some folks typing, so I'll let those questions come in.
Well, I will just ask you a question directly. Just out of technical curiosity, do you folks have any WASM at all in your code base for the web, WebAssembly type of stuff in your web client, or are you finding that the performance with JavaScript and WebGL is just fine?
Yeah, so we don't have anything WASM based right now. that's definitely an area of interest, especially because, again, our fundamental code is C# for the core of the engine. And right now we translate that C# to JavaScript and then wrap it in TypeScript. People are working on various tools to compile C# straight to WASM, which I would love. That would be a simpler build process for us. And, it would eliminate the TypeScript layers where I personally, Python, JavaScript, they're the main languages that I work in, and I write probably 99% plus of my code in them. But it's really nice to have a compiler which tells you when you mistype a variable name. So being able to go from the C# straight to the WASM would be nice. So far, I mean, what some of our engineers have said is that actually the performance gain of that might not be such a big deal because we load stuff into the WebGL state and run the WebGL rendering, but actually, like, the amount of time that's spent in JavaScript land doing computations is relatively low compared to, we're setting up the WebGL and then letting WebGL do its thing. So I've been told that actually converting to WASM might not help a lot in terms of performance, but just in terms of having a cleaner build system, it certainly is very appealing to me. And I do a lot of work in Rust right now, and I'm very excited about Rust to WebAssembly compilation, and it would certainly be pretty cool, but it's not like a front burner thing right now.
Yeah, Rust.
Yeah, I'm a very big Rust advocate, and yeah, I mean, although for a lot of what I'm doing now, building out these kind of fleshing out the web UIs a little bit more, TypeScript is working pretty nice. I'm very impressed by their ability to capture all the ridiculous things that people do in JavaScript into a TypeScript, type system that seems to actually work. So Peter asked, where do the WWT data come in? Is there some kind of network of mirrors worldwide? Yeah, so the data stream off of worldwidetelescope.org, which is hosted in Azure, and we have a CDN layer for some of the most common tile data. So thus far, that's been sufficient. We do pay bandwidth costs every month to maintain the data servers and keep the data flowing. I'm sure, like, I have to admit, I use it in North America. I have a fast internet connection. If you're loading WWT data, in more remote places, there's probably a lot that we could do to improve the responsiveness for the data streaming. I know that, so the China VO group, they've done a lot with Worldwide Telescope. They have their own Chinese version of the Windows application that they use for a lot of education and research and analysis. And I believe they have mirrors set up so that there's kind of a closer endpoint for people accessing WWT in China. Yeah, so continuing on the same thread, are the data for WWT pre-cached in different world regions? If someone in Europe is loading a big image, is it available for anybody in Europe? Yeah, so we have the CDN service, but for our kind of core data assets. But that's the extent of that. I mean, if you're talking about loading a big image, yeah, I mean, fundamentally things have to download to your browser, but the way that our kind of model works is if I'm doing something like exploring that big NOAO map, we've used a Python package called Toasty, where I'm actually trying to encourage people to use this a lot, so I'll type the documentation URL there. Toasty is our recommended Python library for converting imagery into WWT formats. And so you can take a very large TIFF image or FITS file and convert it into the right tiled format and get the right metadata and things like that. Or what we're working on right now is tiling FITS files. And so if you upload those data, for things with those large images, we'll upload we'll do this tiling process and we'll upload that to our central servers, and then, you know, it distributes around the world in a way that we hope is, you know, it's the best that we can do for, you know, sort of the resourcing that we've got. Question about the Noir Lab image. I'll pull it up for you. So I got it off of our WWT user forum, and oops, I think, oh, okay. Sometimes my internet does that. And that's a particular forum thread where we've got folks right now who are working on importing data from a variety of sources. And this is, so for instance, if you have some kind of research grant with some broader impacts, and what you might want to do is help people see any kind of large scientific data that you're showing off, please let me know. We're very interested in helping people out with, you know, I think we're able to help you share data, showcase data, as our slogan goes, in a way that is really exciting compared to, you know, just showing a static JPEG in a static web page somewhere. Dirk asks, is there an option to use spectral axis of Fitzcube to get color-coded Doppler shift rendering? Yeah, we don't have that built in any sense. That's the kind of thing where I'd recommend that you would probably, you know, I would probably recommend that the thing to do would be to write a little bit of Python code to transform your data into something that could render in the WWT view. Overall, I mean, so, you know, being able to do this zooming and clicking on the fly very smoothly, you know, it's a very highly tuned, high performance rendering engine. And so it's there's certain data formats that it can work with and renders, and you know, they're the formats that it works with for special reasons about how they fit into some pretty low level stuff in the engine. And so I would say that, you know, it ends up often being a question of, you know, figuring out how to transform your data into what the engine accepts, because, you know, the engine is highly tuned to deliver the experience that it delivers. So that's what this Toasty Python package, where I pasted the link in the Discord chat. You know, Toasty is intended to be the package that helps you do that kind of transformation and helps you get your data in there. For, you know, we want to support a broad range of kind of fundamental building blocks in this engine, but, you know, there's always going to be sort of there's always going to be more applications where the best approach is to transform your data into what the engine takes. All right, so I think the 2 hours have elapsed. I'm happy to keep on talking, but also I don't know if I haven't honestly paid attention to the schedule of what else is happening today, but this does mark the 2 hours. So thanks everyone for attending, and I'll be maybe taking a little bit of a break today in general, but if you send me a message on Discord, I'll get it sooner or later, and happy to answer questions, and yeah, try and help you see if this can be something that meets your needs. So thanks very much.
All right. Well, Peter. This was a fantastic tutorial. It was really awesome. Also sparked a lot of discussion on Discord and on Zoom. And I think everybody was really impressed. I definitely was. And I think this tool is quite powerful and very, very good for our work and for exploration and all this kind of stuff. So thank you so much for giving this tutorial and also getting up early and preparing. We know that it's a lot of work and we appreciate it. Thank you so much, Peter.
Thanks.
And
all right, I'll sign off. Yeah, I'll sign off now, but I'll pay attention to the Discord and hope everyone enjoys the rest of their day.
Awesome. Everybody else, we resume in 3 hours, unless I'm grossly mistaken, but I think so, 3 hours at 17:45 UT. with the fourth and last training for this wonderful Sunday and first day of ADAS 2020. And again, thank you again, Peter. And you can find Peter again in the next days in Discord. Awesome. See you in a few hours. Bye.